model providers focus on algorithm, and the application developers focus on user experience. They can't consistent easily. So with this problem, how can we achieve? How can we fix this problem? I think we can build a AI stack in the OS. So we built the open-killing AI subsystem. Let's look at the architecture we built. Our design principle is very simple. It's just hide the complexity at the bottom and expose, simplify at the top. Developers should not worry about hardware difference, and the users should not worry about where AI runs. The system handles these decisions automatically. And our AI subsystem has 3 main layers. First is the unified inference framework at the bottom, and the second is the AI runtime at the middle, and at the top is the AI SDK. Together, they create a full AI infrastructure inside the operating system. And first, let us introduce the unified inference framework. It provides a high-performance inference service. It hides hardware difference and supports heterogeneous computing. This means applications can run on CPUs, GPUs, NPUs, and other devices without modification. It contains many models. For example, we can see the Tensor Info LLM, which focused on large language model, and the engine management engines such as OpenVNO, TensorRT, and so on. And with this framework, developers do not need to rewrite applications for each hardware platform. And about the inference framework, we build AI runtimes. AI runtimes is the brain of the AI subsystem. It manages models and resources and execution. It also decides whether a task should run locally or run on in the cloud. And it mainly consists of 7 models, just listed at the right. And the first is the AI Capability Service Center. This model provides core AI service, such as conventional AI service, generative AI service, embedding service, and so on, which support OCR, speech recognition, text generation, image generation, and so on. And another key model is the AI engine. The AI engine connects the runtime with the model servers. It supports both cloud models, on-device models, and the engine uses a plug-in design. This allows users to easily integrate new models in the future, and this architecture supports dynamic edge cloud cooperation, and the system can automatically choose which best execution location. And another important concept is single servers. Instead of exposing random models to developers, we expose high-level capabilities. For example, document QA. This service allows users to ask questions about a document. And behind this, several technologies work together, such as local embedding, vector database, on-device language models, and all document data stay on the device. Nothing is uploaded to the cloud. So this ensures strong data privacy protection. Finally, we provide an AI SDK for developers. The SDK separates the interface layer from the non-link implementation. Developers only call APIs. They do not need to understand the model details. Through the unified API, applications can access capabilities such as natural language processing, image recognition, speech processing, and so on. This greatly reduces development complexity. Now let's show some capabilities appears in the real time, in the real system. These are the AI components and the applications on our OpenKeying, and covering smart interaction, system control, data management, imaging processing, and more. I think the most visible feature is the AI assistant. The AI assistant is the main interface between the users and the OpenKeying. For example, system settings are often hard to find. Instead of navigating multiple menus, you can just simply say, please set the volume to 20%, and the AI assistant will set it immediately. The assistant also helps with other tasks. For example, you can let him write in a weekly report, translate the text from other apples, or generate charts according by your dates. Our goal is simple. It's just make AI a real assistant for every user. And let's show you the video. First, we can set the model, and we can chat with it. And we can change the model to the window. And set the volume of the system. And set the schedule. Okay, and another area we improved with AI is the data management. Traditional operating system organize files mainly by file path, and but users usually remember contents, not the file path. So we built a data manager. This tool organizes files based on the content. And also, let's show you the video. It connects all the files related to OpenKeying, such as the imaging, the files, the doc, and other files. And it can update at real time. Okay. And we also integrated the AI semantic search. Users can search documents or images using natural language, significantly improving information access efficiency. And also, there is a video. And it can search not only the local data, but also the online data. This is the cut. Another feature we built is called the memory map. Memory map records applications activities and browsing history. Users can review past activities using a timeline, and they can search them semantically. By the way, this feature is using only local model. It shows the history. Let me show you the video. It shows the history. And then you can search anything in the past. Okay, so the last is a flexible model configuration. Users can choose between cloud model, local model, or private models. This flexibility is important for enterprise environments. Finally, I will show some lessons we learned. The lesson 1 is to do not expose model details too early. The earlier versions of our APIs were tied directly to the space models, and all models promotes and parameters. When we changed the model, everything broke. So I think the lesson 1 is to do not expose the details. The lesson 2 is scheduling matters more than model quality. Supporting mailing framework is easy, but without unified scheduling, resource conflicts appears quickly. And the third one is to edge cloud cooperation must be intelligent. Simple feedback strategy may bring many problems, such as unstable response. And dynamic decision-making engine is essential. Looking ahead, we believe operating system will become AI native in the future. Users will interact with computer mainly through natural language. The operating system will understand user intent, and applications will cooperate through the AI. To move towards this vision, we are also exploring several new directions, such as the more intelligent kernel and the more seamless interaction. Open source has always been about cooperation. AI will make that cooperation even more powerful. If you are interested in AI operating system, we warmly welcome you to join the Open Killing community. And thank you very much.
Hey, okay, all right. Thank you so much. Let's give another round of applause. Thank you so much, Young Fan. It is time for us to move right along. Breakneck pace is going to be like this all the next few days at FOSSASIA. So if you got somewhere else to be, Okay. What flakes don't let you pin? I'm going to read the bio. It's very interesting. Toastal is a freelance Nix developer based in eastern Thailand. Guys, we are in Thailand. That's pretty crazy. 16 years of software experience.
Oh, it's working.
Give us just a moment here. Nix OS, man. Who here has used Nix? Yeah? Who here uses Debian? Yeah. What about Ubuntu people? Pop OS people? Okay, which of you are Arch users, be honest? Okay, you know, we're gonna have to talk after class. Temple OS? Windows? No hands go up, okay. Mac, okay, we got a couple Mac people. It's okay. BSD, free, open, either. No, okay, we got BSD. Okay, okay, you'll hate it. Cubes or Unix. That was an event. 2 months of my life, man, on cubes. Okay, I think we're ready to go.
All right. So
Let's go ahead and give a round of applause to Toastal.
I would ask if we know Nix here, but after the Geeks talk, I know most of us don't. So that's all right. Let's talk about Nix. What is Nix? All right. So what is this? Do we recognize this? ls at the root. This is the file system hierarchy, and this has flaws, right? So what are the flaws? Let's talk about them. So generally when you have an operating system, you have like a single version of a binary. You have more or less a single version of libraries, and it's on package maintainers to try to keep patches to get all this stuff working as if it were just one snapshot. Yeah. You also have another big problem that is configuration entropy, right? So I had an Arch install once. I did a Pacman update. There was an update to PAM, and I didn't see the pacnew file, and then I couldn't log into my system. That's a problem, right? So Nix asks us one thing. Geeks does too. What if everything were just symlinks, right? That makes some sense. Yeah. So here we can see that the hosts actually points to the Nix store, right? So this actually isn't a static file in the system. So this will change as your configuration changes, rather than you editing this file and then eventually, you know, if this wasn't Etsy hosts, but like the PAM configuration, you won't have that issue, right? So let's talk quickly about sandboxes and substitution. So what is derivation? Derivation looks a bit like this. So you have a name of a project, a build recipe, sources, dependencies, configuration flags, and that gives us a derivation, right? And a derivation is both a file but also a data structure, right? And so we'll take that, we'll hash this derivation with the name, and that will give us an out. Out is an environment variable, which then gets handed into the Nix sandbox along with a derivation like build recipe. And then inside that Nix sandbox, which is read-only and has no access to the network, you can't call time, everything returns 0 for the Unix epic. And what you get then is this pure environment, right? And you're building into this read-only store, which since you can't write to it, you can infer certain levels of purity, right? And so let's talk about substitution, right? So this is something we can understand, this little BC thing. If I know y is 3, I no longer need to compute x plus 2, right? Well, I need to be up all night. And that includes running in the sandbox, right? So this is functional programming ideas, right? So if we know that, we can substitute it. So we know what the derivation is. We know what our sources are. We know what our build recipes look like. That means now we no longer have to build that. We can just substitute it, right? And so a lot of these things are going to be built. If we look back at our Etsy host here, we can see again, we now have what I talked about as the hash plus the name. And if we look at the derivation, we can see everything that's required to build it. This gets hashed. This is how this happens. Okay. And this ends up being trees, graphs, right? So you start with these inputs and those build derivations, which could then be the inputs of other derivations, and building the whole system from, you know, in this case, you'll usually do Nix packages, which includes a C compiler, which includes the whole world, right? And so if I tree my system profiles, this actually includes my whole system configurations too, right? So this is some versions of my operating system. And so these will get populated in your grub or your systemd config, and whenever you boot, you can now boot to a prior version, right? So whenever I said I had that PAM issue and I had to get out a rescue disk because I couldn't get back into my system, in this case, you say, oh well, you boot from an old version. You can also do rollbacks for free because it's all symlinks, right? So whenever you do NixOS rebuild, it's going to build out the whole system, and then it's going to rehook all those symlinks for you. So that makes a lot of sense, hopefully. But what matters is we need to start with inputs, and we need to pin those inputs, right? So before we do any of this, we need to get a version of, let's say, Nix packages, which will include, you know, what version of the kernel, everything down the whole line, yeah? So we need to start with these pure, stable references. Anything impure will ruin this. So if you read some of the Nix tutorials out there, they'll tell you stuff like this. Does anyone see an issue with fetching this tarball for Nix packages? Huh? I don't think so. But the problem is this. So this is a branch, right? And a branch is not very stable, right? So we talked about this graph here. I'm showing it again. So if this NixOS unstable is changing over time, then our sources are now changing, which now means that we have to rebuild this graph. And that's not good for stable systems, right? It also, yeah, so you end up with things drifting over time. So we don't want that. So what did we actually want? Well, if we run git ls remote, we see we have a hash, right? So that is what we want to put in here. So we would take this archive, put in this hash, all right? But we always want to point to a branch, generally speaking, right? We want to be like, okay, give me the latest unstable. Give me the 2511 or whatever the latest stable is, right? But we need that to change over time with what the actual hash that resolves to is. So that's what input pinning is trying to solve. So let's install some software. Software can come from anywhere, including not Git. Wouldn't it be fun if we could try, we were free to try things and not be forced into using Git? Well, let's give it a go. Let's install something visual, a Vim color scheme. This is very easy to see, right? So let's take a look. Here it is. That's a color scheme. Lots of purple violet fans. Do we like it? Is it a cool theme? Too bad. I'm the dictator of this talk. It's cool. All right, so let's install this into an editor. So we're going to pull up this config again. And what is important to note is this is a Nix derivation. And what this is going to do is it's going to create a new NeoVim binary closure for us with the RC file injected. So we can modify this. And as this changes over time, we will get NeoVim with the config we're looking for, right? So the way this is set up here is it says, if this plugin name, Sujilite, is missing from Vim plugins, don't install it. If it's not installed, don't use it as a color scheme. That's what we need to know for this. Okay, so now if we run Nix release, we can see we don't have the theme. That's what we expected. This is pure environment. This is actually using my editor theme. This is a completely separate NeoVim configuration. So it's 2026. What is the modern meta for installing software? Well, we ask the LLMs, right? And what do the LLMs tell us? Use experimental Nix flakes. How do we know an LLM told us this information? Because there's emoji where we don't need it. So now we're going to assume that we already ran Nix flake init. We don't need to know that right now. But let's try to run what they're telling me. Okay, so but first let's take a quick look at what a Nix flake looks like. So in this case, we have inputs. And inputs are, this is the input pinning. So this is the inputs to build our derivation, right? So we're going to need to add a new input, which is our plugin, Sujilite, right? So we've enabled it. This is what the LLM told me to do. And then it said, install these two overlays onto Nix packages, and we should be good to go, right? So let's run that NeoVim that we just talked about. Oh no, input darks HTTPS : blah, blah, is unsupported. So what happened here? Well, if we grep for darks, we can see that we have darks plus HTTPS support, which never existed. This is a reasonable hallucination, but this is not supported in flakes, or a lot of things, right? So if we go out to the website of this plugin, and maybe we'll have some luck here with the network, maybe we're not. What to do about that? It is stuck. Anyways, what we're trying to get to here is that we can use a tarball instead. They're going to offer a tarball, right? So that gets us around the issue here that darks isn't supported because it's not built into the Nix binary. Okay, let's come up with a new plan, because that's not going to work. Or is it? Oh, it's just really slow. Anyways, so if we go back and take a look at that, we changed it. We got the tarball. We pointed the tarball. It's fine. Okay? So we can see here with our grep, what had changed is that, and we ran a sed command that replaced that darks with a tarball. That's fine. Now it's time to update, right? So now if we run nixflake update, we see that we get an update to Sujilite. Okay, that's cool. Let's run nixflake update again. We get an update to Sujilite. Another update. Why? Well, this is dumb, and this is unsmart, wasteful behavior. We are downloading the entire tarball, which could be megs, gigs, petabytes, just to come down and say, oh, yeah, it's the same hash. Cool. Nothing updated. That's wasteful, right? So now we actually hit the title card of this. And this is why this is called Nishtamal. This is a tool I built, and this is about what flakes cannot let you pin. All right, so if I ran a setup, which this is a demo, let's do a split here. You can see we have something here that looks a little bit like that nixflake, right? But we have this new concept here called fresh command, and this will be running your terminal, and it will return some sort of value that can be a canary over time, right? So you can ask it, because there's a lot of things that offer, an Atom feed. The HTML page says what the latest version is, so we don't need to download the whole project. For instance, if I curl this weak hash for the Sujilite input, it now gives me this new hash, this weak hash, as a canary that tells me, oh, something updated, something didn't updated, right? And if I run a lock, hopefully we can have some decent network. Let's see here. It's going to lock this configuration for us. I wish this were going faster. So, I don't really know how to make it go faster. You can only make the internet go so fast. Yeah, well, let's take a look at this while we're here again. So, what this has offered us that the Flakes doesn't is that, look at this, we actually get pure dark support, right? Because we can now get access to the fetchers that come from Nix packages, right? And so if this is the case now, we can remove this input. We can start a new input. Here we can say inputs equals import Nix tamal for niche tamal. We can remove this import. We can import inputs.Sujilite Nix overlay. And then we add the Vim plugins overlay. So there's two overlays. Bop, bop. Looks like this. And let's say we blocked this hubs.darks. Then we would end up with actually being able to so we'll remove our inputs. And we see that we get our configuration that we expected, right? And so if we wanted to add a patch, we can say add a patch. Looks like we're a little bit late on time. All right, and then we can do another prefetch, which hopefully can be a little bit faster. And so some of the other features that we can do, so we have mirror support. We have the ability to support inputs like darks, phul, fossil, and anything else in the future that aren't supported by the Nix built-ins. We can do eval time versus build time evaluation for our inputs instead of being limited to just eval time. And we can also support changing the hash algorithm. Blake 3 exists, can be supported. And let's see here. But none of the other tooling supports it. It's listed as an experimental feature, but we can see that when I run Nix run, it's going to build the project. Query missing path. And download. Running the fix up. Yeah. and we can see that we can actually patch things on the fly. And this matters because we can actually patch Nix patches on the fly. So we can avoid the chicken and egg situation that you can't see in other tools, right? And so I would show you a thing end for the title card, but we are out of time. So this Nishtamal, if you'd like to learn more about Nishtamal and Nix and why flakes might not be what you want to use, give me a shout at lunch.
You going to be outside available for questions? Absolutely. Okay. So if you do have questions, we don't generally have time for Q&As here. Go ahead and head out into the hall and do the questions there because we are moving right along. Nanwoo, go ahead and come on up here. We got another talk. This is the last one before the coffee break. This is fusing AOSP, is that how you pronounce it? And Linux to open a new chapter for Linux desktops. As a person who struggles with Linux desktops daily, I'm open to new chapters. Nan is the development lead of the OpenFDE project and has 20 years of experience in large-scale development. We're about ready to go. After this one, we are going to be taking a bit of a coffee break. So you'll have time to get out there, use the restroom, shake some hands, do high fives, and all that kind of stuff. The schedules do change over the day, so if you go to summit.fossasia.com, I do recommend, like if you have a tab open and it's cached, I do recommend refreshing the page just to make sure you have the most recent schedule. Because as an example, we did move things by 5 minutes because of the group picture that happened in there, and sometimes speakers get sick or cancel or whatever the case, so do remember to refresh the schedule. Oh, well, that depends on if you have JavaScript enabled. Not everyone does. Some people use Tor on mobile like psychopaths. All right, we ready to go? Then I will go ahead and pass this off to Nanwoo. Let's give him a great big round of applause.
Good afternoon, everyone. I'm Wu Nan, maintainer for the OpenFDE project from China. Today, I want to share with you a story about OpenFDE. A new exploration for the Linux desktop environment. Today's talk will unfold in 4 chapters. Let's dive into part 1, the Linux desktop challenge. Let me start with a question. Why does Linux remain stuck at a low market share on the desktop? Let's examine the essence of the problem. I call it the app gap paradox. On the server side, Linux dominates with a commanding 96% cloud market share. Yet on the desktop, it's stuck at less than 5%. What's the fundamental bottleneck? It's the severe scarcity of the application ecosystem. On the Android platform, boasts 3 million apps. Meanwhile, Linux native apps number merely around 5,000. This isn't just a gap. It's a generational divide in ecosystem maturity. More importantly, there's the mobile-first exclusion effect. Modern collaboration tools prioritize mobile and web, completely bypassing native Linux versions. For developers, the Linux ecosystem is a fragmented hell, and the packaging nightmare across distributions. This creates no commercial incentive for developers. Faced with such a massive ecosystem, the solution seems obvious. Why not bring Android apps to the Linux desktop to fill the void? It sounds perfect, right? So the industry tried various solutions, but how well did it work? Why existing Android on Linux solutions fall short? I will identify the 3 mainstream approaches and their fatal flaws. First, the virtual machine approach, what I call the fortress problem. It's like an isolated fortress. Secure, yes, but at a tremendous cost. Second, the translation layer approach, like playing the lottery. Compatibility hovers around 17%. Whether your app runs is pure luck. Third, traditional emulators like the glass wall. You can see through it, but you can't truly integrate. All existing solutions treat Android apps as guests rather than native citizens. Since existing solutions don't work, we need to rethink the approach. This is what I want to share, our vision. Our goal isn't merely to run apps, but to make Linux a first-class citizen for modern application ecosystems. We aim to achieve 3 core objectives. First, seamless fusion. We want apps to be anywhere their guests. They share the same file system, the same clipboard, and direct hardware access. Second, unified development. Developers no longer need to fight fragmentation. You can use the mature Android Studio toolchain to build apps that run both on Android and our Linux desktop with 0 extra cost. Third, performance first. We deliver better mental speed. To realize this vision, we promptly introduce OpenFDE. OpenFDE is not just a software. It's an OpenFusion desktop environment. It deeply embeds the LSP Android open source project window management and graphics stack into a standard Linux distributions. It introduces the massive Android ecosystem to Linux, while fully retaining the powerful underlying capabilities of Linux. So how is this fusion achieved technically? Let's enter part 2, architectural deep dive. Focus on this system architectural diagram. First, the foundation. We dock LSP onto the standard Linux kernel using RxC containers. This means Android apps run directly on the Linux kernel, enjoying native performance. The critical innovation sits in the right, FTX11. We will implement an X server into the Android framework. What does this mean? Traditional Linux apps run directly. Traditional Linux apps can seamlessly plug into LSP framework, run as Android Windows. Then look at the fusion layer. When we implemented the file system fusion by directional clipboard and hardware bridging, there's another crucial breakthrough: graphic rendering acceleration. I'll explain this in detail shortly. Next, details on the FTX11 architecture, our core mechanism for window fusion. Step 1, we implemented a complete X window system on the Android framework. This receives and processes X protocols from Linux apps. Step 2, we built a base window manager that map X window layout, appearance, and behavior directly to LSP's native window management. The final effect: Linux apps run OpenFDE in a native manner. fully integrated to LSP Windows system. With window management solved, the next challenge is performance, especially graphics performance. As you know, Android uses the Bionic C library, while Linux uses the GUC library. There's a natural barrier between them. OpenFDE references the lab hybrids approach. We modified the OSP by Bionic C dynamic loader to natively support loading Linux glib C versions of related labs. What does this mean? Android apps can directly call Linux GPU drivers. Performance has only minimal overhead. It reduces the GPU drivers. Beyond the graphics, we've implemented comprehensive device bridging. On our Android HAL implementations, we use bundle cross-process calls to directly utilize Linux-side libraries to drive hardware. The actual effects are remarkable. Take network bridging. When you open a VPN app on the Android side, Linux app auto-connect through this VPN without any configuration. This is a godsend for developers. Similarly for audio, camera, and Bluetooth. Next, our approach to application compatibility. As you know, Android was originally designed for mobile, single window full screen mode. OpenFDE transforms it into a desktop-oriented multi-window mode. This transformation inevitably brings compatibility issues. We have abstracted common compatibility issues into 10 configurable completely flags. Users can check and uncheck this based on specific app behavior, taking effect immediately. That covers the technical architecture. Now let's see OpenFDE in real-world scenarios. Let's look at 3 typical daily usage scenarios. First, office productivity. Second, entertainment. Third, gaming. No more worrying about the lack of Linux games. For developers, OpenFDE brings revolutionary convenience. For developers, you can use Android Studio natively on the Linux desktop for development and debugging. More importantly, this is an industry milestone. OpenFDE is the first platform to publicly support compilation for the ARM Linux version of Android Studio and its full toolchain. Now you can develop native Android tools ARM Linux. By the way, these screenshots came from a PC running on Factorium chip. Of course, we won't stop here. OpenFDE is continuously evolving. Here are 4 priority directions. Finally, OpenFDE is a fully open source project and we sincerely invite more developers to join us. We believe the next desktop shouldn't be a wasteland, but a fertile ground for creation. Let's make Linux a first-class citizen to a modern ecosystem together. Thank you.
We got 3 minutes for questions if you want. Do you want questions? Are there any questions? Yes, yes, we do have a couple. Okay, just a moment. Let me run these over. Raise your hands again. Okay.
Hello. You mentioned that you have Bluetooth bridged between Linux and Android applications. Do you use BlueSD as a host Bluetooth stack, and you implement Android Bluetooth Hell on top of that, or how does it work?
Sir, may
Okay. Yeah. So maybe afterwards you guys can
Yeah,
go
okay,
to the
okay.
hall and you can.
I'm wondering about Google Play services and Google Safety Net, especially also. Can you share something? Have you tried running them? Do they work? And also the Safety Net attestation.
Still difficult? You understand? No, you don't understand?
Maybe I
Okay,
help. Yeah.
So none will be available
I
afterwards.
translate for Chinese for him. 他问那个 about GMS Google 就 GMS Google 服务的嘛。Yeah.
可以启动的。
是可以启动 Google Play Store 是吗？那比如说有一些游戏像英格尔斯，他们会要求有那个 Safety Net，那个可以过吗？
那个没有单独去看过。
He said that the Google Play Store is works, but no safety net.
Okay, you guys are hired? Yeah, if you guys, afterwards, if you guys wanted to head out and chat, that would be great. And if you guys could stick around and help translate, that would be awesome. Okay, I have 2 microphones because I'm very important. And with that in mind, thank you very much. Let's give a great big round of applause. Anyone who has questions, go ahead and head on out there. Guys, we are about done. I'm not going to be emceeing anymore. I know, very sad. But there's going to be another MC coming in next time. It's coffee break time. Head on out there, grab some food, grab some coffee, use the restroom.
Next session starts at 1:30.
The next session starts at 1:30, so it'll be about an hour. Can I get you to take a picture of me up here so I can send it to my wife?
future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells, I love you so much, earlier than ever before, and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells, I love you so much, earlier than ever before, and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, And I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption, we do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption, we do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells,
I love you so much.
earlier than ever before, and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells,
I love you so much.
earlier than ever before, and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have 2 sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have 2 sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
Hello, good afternoon, everyone. Welcome back to the OS session, FOSSASIA 2026, Bangkok. Operating system is one of the most hardcore area in computing, and they are the layer to allow us engineers to talk with the machines. So that's quite important, even in this future of AI era. So let's begin. And our first speaker is Praveen Kumar, Principal Software Engineer at Red Hat. Praveen is an active contributor to many open source projects and has been a featured speaker around the international conference. So today he will talk about creating custom Linux images using bootc, right, and Parliament desktop. So let's please welcome Praveen Kumar. Thank you.
Thank you. So my goal is to keep you awake after the breakfast, right? It's quite hard. So I'm hoping that so this session is since I have only 15 minutes, so I kind of target is 10 to 12 minutes. Maybe we'll go with the kind of technicality of how the bootc and Podman works, and then I have a very quick demo, and then we'll go with the question answer. So how many of you actually know about containers? Just can you okay, so there are a lot of people. Do you know anybody about the bootc, like the bootable containers, right? So okay, so there are 1 or 2 people. So the people who are in the admin side of the things, right? They know how hard it is to create a kind of a different or customized distribution which you already have. If you want to distribute it across your organizations, right? So what you, till now, actually, there are multiple ways to do it, but in the traditional way, the thing is that you have a different set of tools which you use to create those customized customize operating systems, and then you give it to your organizations to work with. And to do that, you need a platform-specific, that particular requirement of the hardware. Like, okay, if I want to create a Fedora-specific distribution, I'm supposed to have the host actually running Fedora, and then I can use the kickstart files and then do that. So it's very hard to reproduce, and creating this end-to-end CI/CD pipeline, which is continuous integration and delivery, it become very, very hard, right? So now the container technology came, right? Now most of you already know about the containers, and it is now, I think it's more than 10 years or something, where this technology is like gained the popularity, the way the application developers actually shipping the applications, right? Before, it used to be the case like something works on my system might not work to the, when it goes to the productions, that particular system, it doesn't work. But right now, it's like, okay, I'm giving you the container image. If it is running on my system, it's supposed to run end to end, right? And then it's become very easy to create this CI/CD pipelines around it. So if you actually use any kind of a hosting platform like GitHub, GitLab, or whatever, right? They right now, like GitHub have GitHub runners, they have GitHub Actions, which you can use and end-to-end create this complete end-to-end pipeline. You can create the image, you can upload it, and all those kind of things. And another important part is this cross-platform. So how many of you actually right now not using Linux? Not using Linux. Okay, everybody's using Linux here. Good. So right now, so the thing is that most of the organizations, like big organizations, they kind of have a contract with the different operating systems. Like most of them are using Windows, and then they are saying, okay, do I really need to like use that particular operating system to do my work? But right now the tooling is so easy, it doesn't need to be bound with the operating system, right? You can use the cross-platform to work with it. So okay, so now the bootc, what is the bootable container, right? So you know about the container technology. So in the container, what happens is so you create an image, and then you use the container runtime, and then you run that particular image, and then you see if your application is working or not, right? Now, that image which you create, it doesn't include any kernel on it, right? So what you have, your only application layer. The kernel it shares is the on host where the container runtime is running. That's the kernel it shares, right? So now with the bootc, what we have is, it is using same technology, so it's a OCI image format, right? And then the biggest difference is that particular image actually contains the kernel also. So you have the kernel, you have everything, and then you have the tool of bootc. So when you create the image size will be big, sure, because it has the kernel. But when you try to run it using the container runtime, it will run as a container only, the same way your image is running. But you can actually create this particular image to bootable systems. Like you can create a different kind of image, like QCOW2, AWS image, AMI, GC, or whatever. So as I told, in how it works, so you can actually create, so the way you create your application container image, right? You create a container file or Docker file, whatever you say. And what that has is the kind of specifications, like, okay, this is my base image, and this is my application. If you want to compile it, you can do it in the build time, and then you can add it. You can have multi-layered image also, right? So all the things you can do it here, because it's the same thing. But if you see here, when we build it, then only the host kernel is used, but when we run it, it doesn't use the host kernel if you are running it on the VM. I think this, I'll come back on the second slide later, but the thing is that why we actually require it, why it is an important thing, because the currently what you do is like, with the application container, if you think about it, you have the container file, you create the image, you push it to the container registry, right? And then you use that container image from the container registry, and you can update it using different versioning way of things. But that's all about the application container side. Now, but what if I'll tell you, like, in the system or bootable container side also, you use the same things, but the good thing is now, once you deploy it, and then if you want to update it, you don't have to again kind of redeploy it. You just have a tooling inside it, which you can directly use the update, and it will take the things from the container registry and update to all the platforms, right? So your system updates becomes very easy. It also contains the rollback. So assume that a new version didn't work as you expected. So you can actually able to roll back it using the bootc command, which we'll show in the demo also. The file system layout. So the file system layout, the work it will do is like, when you run it as a operating system, then these are only the read-only at the runtime, except these two, where you can actually put your data, or you can change the files. But other than that, there will be all the directory structure which will have is only the read-only directory. So, but if you see here actually you can install the packages, because that's a build time. That's where your specification is. This is a simple container file you are showing here. Like, so if I have a package, assume that Vim, and if my system is running and I want to install another package, I can't do it. I have to go back and do the change here, because this is the only source of truth, and then update it back to there. And there are a lot of, like, if you want to see, like, okay, what all the restrictions we have on the file system layout, you can check this URL. Now about the Podman desktop. How many of you actually know about the Podman, what Podman is? Okay, so it's kind of similar thing, right? And how many of you use Podman desktop by any chance? Okay. So Podman desktop is similar kind of a Docker desktop. You can use it. It's provide a UI for you to use it in any platform. And it's a kind of provide you a UI for your container workflow. It has the already extension around bootc and Podman, and you really don't need to be run that tool on Linux. So if you are using different operating system, you can run it, and you can try it out, your changes, and you can actually see if that works. So the demo which I have is recorded one. I think, 1 second. And before we go to demo, this is what I want to show in the demo. This is the outline of particular demo. Like, what I'm going to do is that I'll create an image which is have the HTTPD service running. It's a very basic demo. And then and everything is working fine on that particular HTTP service. Then we'll update to version 2, which has the broken thing. And then when we see that there is a failure, we'll do the rollback. And then we'll again see that, okay, we are back to version 1. And finally, the Apache server is running again. So the purpose is that it want to show that how the rollback works and how the update actually works without actually doing anything like the old way of doing things, like reinstalling or whatever, the way we want to do. So this is the container file. So I'm putting the container files also version. This is the first version of the container file. It has like the base image is coming from the Fedora bootc. So here also like we have Fedora sent to us with the community, like we have these bootc images which you can use, and then you can kind of try out like how the bootc works. And in that particular image, which is the base image, it has the minimal packages. So whatever you want to install, you have to put on top of that. So right now we are adding the HTTPD service, like we are saying. So we have that, and it's just I'm just putting a simple HTTP running on that particular index page. And this is the second version of that container file, where I'm putting something invalid stuff in this HTTP config directory, which means like, okay, when the HTTP service run, it will not even start because of this invalid directories. So now I have these two things. I'm using the Podman desktop to build the image, right? So I build the image. I'm using the container files, which I already showed, like version v1 and v2. I'll give the image name. I think that's everybody's familiar about how to build the image with either of the any container technology, right? So we build the image. It's building. This is the prompt you are getting. Once you build the image, we have something called Podman plugins, Podman desktop plugin, which is bootable containers. In that, you can actually create a disk image. I want to pause here. I want to showcase like how many disk image type is supported. So once you create the image, out of that image, you can actually create raw image, you can cook out to image, ISO, and all those kind of GCE, AMI, whatever you want to do, right? So I'm actually recorded this demo on Mac. So we want to create the raw image which Mac support. So the other thing is that when we are creating the image in the old time, you know, in the Kickstart files, you provide the users, passwords, and everything. Here we have this options to provide like the build config, where you can provide what is the user by default when you start it, any AMI or anywhere, what will be the default user will be. And if you have any SSH public key, you put it there, and the group also. It's already in. So we have everything there, and then image is created. So this is the first image when it's running. You can see the service is running, right? And I can actually get the version, and bootc version also it say. The other part is that the next thing I'm doing is the switching to the different image, which is the broken one. And that will run, and it will showcase as soon as I go in. It will see that the service is failed, right? And because of that, I have to roll back. So I'll use, again, the rollback command. And this is the VM. It's not the container which is running, it's the VM which is running. So I roll back, I'll again start it, and I'll again check, and it's again back to running state. So, yeah, let's see. So that's it. I have, the time is not permitting, but so here is all the resources. If you want, so the current repository is like very basic thing, but if you want to go much more details, there's another presentation which I had recently. So there I already put some demos and everything on the container file side. So that's, thank you.
Great, thank you, Praveen. Wow, so great.
If you have any question, we can go outside and we can talk about it, right?
Yeah,
so
because
thanks.
I'm also an OS engineer, so normally we will use container. Well, we love container, and now we see the bootc we can use container. It's quite amazing work, and so thank you, Praveen. Yeah, and is there any? I think there's one question. is there anyone? Okay, yeah, there's one. Yeah, thank you.
Okay. Does the bootc or the container stuff have some mechanism for delta upgrade, like between version 1 and version 2 we generate only the delta?
Yeah, so the question is, when we do the switch, right, does it delta or is it like coming from, like it's download the complete set of the image, right? That's the question? So assume that, so right now there is two way of thinking it, like if you have image, right, if you are using container image and you are using a specific tag, assume that the latest is the tag of your image. If you update anything on that latest tag and repush that image, right, then it will only grab whatever you did update. But if you completely do the switch part, when you do bootc switch and switch to something different image, like another version completely, then it will pull the complete version, that particular image end to end.
So the delta image is possible under the same tag if configured correctly, or?
So we can talk outside.
Okay.
We'll show you like how it's actually, because right now in the demo, I use the switch, it's downloaded end to end. So, but we can show outside like how this delta works there.
Okay.
Yeah, thanks.
Yeah, thank you.
Thank you. Okay, thank you, Praveen. Thank you. And so next speaker is Wei Cheng. Yeah, and he's an Android OS engineering manager at IEI Integration Corp. And Wik is a Linux Android BSP engineer and an active contributor to several open source communities, including AOSP and the Linux kernel upstream. Today he will shape insights on NPU performance, profiling in Camry-based AI application. So please welcome Wik Cheng. Thank you.
Okay, thank you. Good evening, everyone. So, because there's only 15 minutes, so let's get started. Okay, I introduce myself first. My name is Wik, and I work for IEI Integration Corporation. And I very enjoy to contribute the software to the open source communities. So maybe you can find my name in some famous communities like AOSP or Linux kernel upstream. And here's my co-author for this section, and his name is Jason Yang. He's a camera expert. So about the camera parts of today's section is all made by him. And about the agenda, firstly, I want to share the motivation for this section and introduce some basic CNN model-based NPU. After that, I want to share the most important part in this section. I want to compare the proprietary driver and upstream drivers difference for NPU. And because today's target application is about the NPU inference with the camera streaming, so I also want to share how to select a suitable camera module. And the next part is summary and future work. Okay. So about the motivation, as you know, the CNN is not a novel design technology. Maybe it's popular over 10 years or 12 years, I think. But NPU is very popular recently and more useful because it's very easy to see the performance is better than the CPU inference. So this is why the HAI inference latency is often disappointing, because most of the application is adopt CPU inference. So when I choose NPU for our inference application, I also want to look for the bottleneck of inference latency. Okay, so I want to introduce some basic CNN model-based NPU. I just list the some popular industrial HAI platforms like the NSP, Rockchip, Renesas. And as you can see, they are all use different NPU IP inside the SoC. So it's a big problem because their driver architecture will be different. But fortunately, they are all support the CNN model. And I also just list the LLM support status. Only few SoC that support LLM model, but I think it's a trend. more and more SOC will support LLM, but it's not today's topic. We will focus on the CNN support status first. And if you want to run your CNN model on NPU, you need to prepare some prerequisites like the hardware support for the left side. The CNN, some CNN important components like the convolution, renewal activation, or pulling some math formula need to transfer to the digital circuit design for the NPU, then it will speed up the performance. And the right side is that I just want to notice that about the TOPS is not everything for the hardware specifications. I will show my validated result later. Utilization is more important than the TOPS. Okay, let's talk about the proprietary driver and the upstream driver. I will separate two parts. Let's check the proprietary driver first, the left side. The pros is high performance because the vendor will optimize that. And if you got any problem, maybe porting issue or application issue, you can feedback to the vendor. They will provide the official support. But the cons is fully open source, always fully open source. Okay. And you also need to get the vendor tool from the vendor and transfer your generic model like the TensorFlow Lite to the specific format model. Maybe the Rockchip has the RKNN model and the NSP has EIQ model. So it's a little bit inconvenient. It's a problem. And after that, you can check the right side, the upstream driver, the process is fully open source and the long-term support, of course, because it's already on this kernel upstream. So you can fully modify. But the cons is that the performance is non-optimized, but it's still improving by the maybe maintainers or some contributors. And if got any problem on the upstream driver, vendor cannot provide you any support. But I think we have another way. We can discuss with the community. Maybe I think the maintainers will provide some useful suggestion. I had the experience before. Okay, and here is an example about NSP IDAMX 93 platform. And as you can see, even if it's the same NPU, but there are two different kind of drivers architecture. It's different. Yeah, we can check the proprietary driver on left side. Actually, the vendor just provide a firmware file. The driver is packaged inside a binary firmware file and running on an MCU, then communicate with the NPU. So you cannot observe any calculate behavior on the driver because already be hiding on the vendor. But when I run in the MobileNet V1 model to test the inference time, and as you can see, the inference time, it is really better than right side upstream driver. Yeah, it's 3.8 millisecond, and the upstream driver about 5.2 millisecond. Not only for driver, you also need to prepare a dedicated library to bridge the NPU driver to run in the NPU. Then, as usual, the vendor will provide you the proprietary libraries. Of course, it's a binary libraries, not any source code. And about the upstream libraries, fortunately, Mesa community already did this project to support. Its name is libteflon shared library project, and you just download the source code, compile it. One library can support IX8 Plus, IX93, RK3588, 3 platforms. Just one library is very useful. And I also integrate two kind of libraries inside our company's project, like the Yocto or Ubuntu source code. If you are interested, you can just download it to study. It's fully open source. Okay, so we already confirmed the NPU inference is better than the CPU already, so we can calculate the actual FPS is about 263. using a mobile net V1 with the input static image. Okay, looks not bad, but when I trying to bridge UVC USB 2.0 UVC camera, then to the NPU inference, the FPS is only 30 to 38, I think. It's no good. So this is why I want to starting to look for the bottleneck. I think it's not only for the NPU or the CNN model. Okay, so this is my validated result about the different NPU inference time. And as you can see, the blue color bar is proprietary driver, and it's better than the red color bar. Yeah. So, but I think it is a special case about the IS-93 because their performance is very close. So in this case, I very strongly recommend to use the upstream driver. I also want to special thanks the right side, Mr. Tomio Vizoso. He's a NPU driver engineer and maintainer in the Linux kernel upstream for the NPU. So this red color bar driver is all made by him, and the Mesa library as well. So he gives me so many useful suggestions for this session. Okay, so how to select suitable camera module? For now, we already know the FPS performance bottleneck, not just the root cause, not just for CNN model or NPU tops. The camera interface or format, resolution, even ISP or non-ISP sensor will impact the performance. And here is an example. As you can see, the MIPI CSI interface, the speed, the throughput is better than USB 2.0. So I just connect MIPI CSI camera, and the FPS is about 70. It's a very good performance than the left side. And if you want to test some popular camera module like the Raspberry Pi camera V2 or V3, you also can use the software ISP solution for using OpenCV because it's a non-ISP sensor. We call it a raw sensor. But it has a problem is that the output image is just the raw data. We call it the bare data. So I will give you some example. If you just output the bare data to the NPU, you can get the better performance, like FPS is 64, but the color is monocolor only. Yeah. And you also can transfer to the RGB converter. The OpenCV has API can be calling. Then you can get the maybe green color shift image. But the FPS will be decreased about 55. And if you want to get the best color quality, you also need to transfer white balance function. Like the OpenCV also provide a function like that. And after up to the NPU, you can get the perfectly the image color. But the FPS is decreased only to 48, I think, about 48. But the summary that is the trade-off. It's a trade-off. Our customer in this case is they can accept this FPS, then with the perfect color. So they can save in the hardware cost because you don't need to add the additional ISP chip. Yeah. Okay, so let's summarize in the future work. About the camera part, the bottleneck is not just caused by the model alone, and the high-speed bus, negative reduced inference performance impact. And about the NPU part, upstream driver is preferred if latency is different, it's minimal. like the IS-93, I think it's a very useful and for the upstream driver. And the vendor driver for the max performance, but consider maintenance cost about the security update or SBOM. You can imagine just the vendor provide you the maybe binary file only, how to maintain the SBOM. It's a very big problem. Okay, about future work, I will support more and more cameras, even HDI in function, and test the real world models, not just the mobile net, like the YOLO ImageNet. And I also want to test the internal ISP inside the CPU. The performance should be better than the software ISP. And I also starting to explore the LLM-based NPU. Hope I can share some good topic next year at FOSSASIA. Okay, thank you. Thank you.
Okay, thank you, Chen. Wow, great. And I think we still have time for QA for one question. And is there any question to show up? Okay, maybe I ask one question. Yeah, because I'm curious about this thing. Wow, that's great. And what's the most surprising difference between open source NPU and the priority NPU? Yeah, okay, thank you.
You mean lead?
Yeah.
Okay. Your question is explain
about
detail?
Yeah. Just a little more about open source, understand open source NPU and the closed source NPU. The
because
driver.
they are the same NPU, the same NPU, just different driver. Yeah, because the vendor will provide the. Sorry.
Oh. Okay.
Thank you.
Looking at the time differences and all those kind of stuff, I wonder if the vendor, they provide any documentation for the hardware, because we may have different interrupters, interruption that might masquerade the performance, especially for serial devices like the camera. So do they provide any documentation that we could use to improve the driver, the open source one, or is just the developers are doing like...
You mean the upstream driver?
Yeah, no, the vendor.
Oh, so vendor driver.
Yeah, the vendor, the IC, the device, the vendor. Do they provide any documentation of their architecture so that we could take a look at those things to try to troubleshoot, or we need to do reverse engineering to write the driver?
Okay, it's up to the vendor. Some vendor will provide the documentation like NSP, but Roadtripper, no. That's always up to some different vendor with different feedback. Yeah.
Okay. When you're doing your investigation, did any signal processing to see if the performance, if it was interrupters or the serial problem, or if you had I/O issue, network bandwidth?
Network bandwidth?
Yes, the bandwidth,
the
network between your device and the IC itself.
Yeah, it's a very good question. Let me check. Yeah, for this example, yeah, because how to say it's better? For this one, we can check the upstream driver. The NPU will start from the Cortex-A and communicate with the NPU directly. But as you know, the Cortex-A's inference is no good. So about the provider driver is changed to the MCU to communicate with the NPU. Yeah, and but it has a trade-off. If you choose the provider driver, your MCU will be occupied. Yeah, and if you choose the upstream driver, you can use the MCU to do other applications. Yeah, like that. Yeah. So the interface is, I think, is using different interface to control. Like you use the SRAM and the DRAM, and this use the shared memory. Yeah. So it's a different throughput, I think. yeah, it's a root cause. Yeah, one of the root cause. Not all. Yeah.
Okay, okay. Thank you, question.
Thank you,
Wei Chen. Yeah, a great talk. Thank you. Yeah. Now, our final speaker is Daniel J. Blumen. I have to say, I think I'm not the first one to say it's a very cool name. Yeah. And Daniel is a developer at Quora.org, and he brings over 2 decades of experience. And he also is our old friend in FOSSASIA, right? Yeah. So I will leave the time to Daniel. Yeah.
Yeah,
So
thank you, guys. Yeah.
Thank you very much.
All right, so I'll talk today about Linux on ARM laptops, and it's not going to be about servers or mobile. It's indeed just laptops, which is the kind of I like where things are changing, I think, rapidly these next couple of years. So I'm an open source developer. I'm also like in my hobby, and a closed source perhaps in some of my work. But I like a bit of kernel work and contribute upstream, application layer like in Golang for web things, and work on like platform bring up often. So 30 years ago, I had one of these. It's one of the earliest ARM-like computers, desktop, 30 megahertz. Since then, things have changed. Now there's 3 x86 vendors, of course. We know Intel, AMD, and VIA. So, and now there are eventually 4 ARM vendors producing like chips for desktops and laptops. Of course, there are hundreds for mobile and embedded systems. So I think this is an interesting thing that changed the last maybe year or 2. So that would be, let's see, MediaTek with their Chromebooks. That would be Qualcomm with their previous generation chips, and now the X1 and soon X2. And then also there's NVIDIA with one of their workstations that you'll see later. And Apple, of course, with all of their M1 to M5 series, which are very innovative. And so ARM, of course, is a big thing in this space, like for laptops. Just that very few people right now have ARM laptops. Of course, in smartphones, it's all ARM these days. And of course, 80% of that is Linux. The rest is iOS. 30% of that is Qualcomm. So they're like one of the biggest vendors producing system on chips for phones. What this means is that when you like have a laptop with something like that, one of these chipsets, they can reuse a lot of the devices, the USB-C retimers, the power management ICs. It makes it easier for bring up. So they have actually 126 system-on-chip variants, which across like 9 platforms, which are maintained by Qualcomm and a community. So it's a fairly large number of files in the kernel, and so it's kind of I want to give you an idea that it's a fairly sizable ecosystem. So. The good thing about Qualcomm is they'll actually post patches at their system-on-chip launch. So here, 2023, they posted the first patch to enable the X1 Elite. And so, of course, it doesn't get taken in the first iteration, but after a few months, after some improvements, gets taken in, and then there's upstream kernel support. So, in this particular X1 system on chip, it's broken down into, of course, different blocks. The main thing, though, obviously, is the CPU. In this case, 12 high-performance cores. Now, there isn't any hyperthreading or anything like that, so you actually have dedicated cores across 3 clusters, GPU and NPU. NPU, that's something which a lot of laptops only they didn't have until recently. So that's for offloading like matrix operations for AI inferencing. Of course, you have image processing and I/O and things, PCI Express, power management here. So I'll go into a couple of these things in a second. So x86, it's a very, very difficult market because it's mature, and a lot of vendors produce code, software, optimized really for this market. So entering that market is really a difficult thing. It's if you have a new laptop, a new platform, it's extremely it'll take time to get in there. A lot of the times, people focus on benchmarks, single core, multi-core benchmarks, rather than the kind of experience, the battery life, or for example, the upstream support in the kernel. So often, you'll buy like an Intel laptop or AMD laptop. If when you suspend it, it doesn't suspend correctly, or there's certain issues. When you run Linux, Windows probably fine. So these are some of these challenges, not only though with ARM systems. Apple, of course, it's an end-to-end ecosystem, so they have a very, very good support for their ARM system on chips in their OS. And there's been some development on running Linux on those as well, which is gives you like a really nice laptop with a bunch of things not working. It's improving. For the X1, I mentioned it's 12 high-performance cores. That's in a 23-watt package. Now, if you want 12 high-performance cores, you're going to be looking at something like a 40 or 50-watt package for an equivalent x86 processor. So you're getting kind of a lot of power there out of that. But not only that, though, I'll talk about the integration of the GPU and the NPU as well. So typically you might have, say, like 4 high-performance cores with threading, so 8 threads, and then 8 efficiency cores. Maybe it's higher these days in these latest Intel generations. ARM also produced their own cores, which are not customized like the X1 cores. So there'll be other systems with these X925 and C1s, which will be emerging this year, and actually already some of them are in the market, like laptops and desktops. So what makes this cool and sort of more efficient over a classic x86 laptop? Well, the GPU, NPU, and the CPU all share memory. And the DRAM is tightly integrated, and it's coherent. It means you don't need to copy data to and from your GPU. There is no PCI Express involved. Now, that is actually quite high latency. So the integration is into like a kind of a first level on-chip mesh. So it is very, very like scalable. There is a more recent standard called CXL, which allows you to have coherency with GPUs. That's something which is emerging in the server market. So there'll be, in the coming years, there'll be more solutions around that for better efficiency with your GPUs on servers. So currently, what are the issues? There was this big effort with Windows on ARM that was like perhaps spanning almost like 8 years or longer. And so with that, if that didn't happen, we wouldn't have accessible laptops in the market with ARM chipsets. And so those are now available. So I have to thank Microsoft for that. I'd say, in general, these laptops would represent around more than 30% additional value. Interpret that as either, say, battery life, or it could be, performance, the weight of it, lower cost. So this laptop is about $1,000 US. I'll talk a bit later about it. Of course, Windows has also a lot of translation. So a lot of code isn't natively compiled for ARM64, so it has to be transpiled real time, cached. Also, it runs with 4K memory pages. So Linux you can boot with 16 or 64 kilobyte pages. One of the issues with Linux on Mac or Apple laptops is that they have 16 kilobyte pages, and that breaks a compatibility with a bunch of libraries, but largely isn't a problem these days. And having the larger pages is more efficient. Okay, so this laptop, it's 70 watt-hour battery, and I get about 8 hours runtime out of it. That's actually using it. The idle runtime is maybe, I'd say, about 11 hours. Of course, there's always a few kind of issues here and there. When you suspend and you resume, you see this kernel warning here. So I'm working also with some of the issues to then fix some of them and post kernel patches upstream. There's the camera doesn't work actually, so that's something which Qualcomm is posting patches on, and suspend is missing on some of other laptops. So you close the lid and it's still on. Also 5 watts at idle. Now that's actually quite high for an ARM system, which is basically derived from a phone, or kind of like a sort of efficient point of view. So some of these things, actually a lot of these things are going to be addressed soon. So something which is really amazing actually about this, it's part of the ARM 8 specification, is by default everything is virtualized. Sorry, not virtualized. As in you run your OS under the actual firmware hypervisor, and so it runs at EL1 here, this OS kernel here. So when you install Linux or when you boot Windows, you're getting that kind of already virtualized OS in there, that area. That actually allows you then to have other, more secure control over different domains. And that's actually part of the firmware, so it's integrated and maintained by Qualcomm in this case. In other words, you'd typically have to run a VMware or Xen or something like that. So that's actually built in. As I say, you actually, if you want to get to EL2, for example, if you want to run your own virtual machine, then you have to boot with some different parameters to then unlock that. So that's actually like a kind of virtualization, virtualized by default, which is actually very powerful. So this year, there's going to be some improvements this year on the X1, namely power saving. So I sent a patch upstream for power saving for additional sleep states. One of the issues, though, is that, of course, Qualcomm is already working on it, just they haven't organized the right structure of the patches. So it then didn't make it, but then they'll be submitting that series soon as well. That'll actually, so that plus PCI Express power saving will also give you about 2 watts of additional power saving, which means probably you're going to get 18 hours runtime out of this thing. Later this year. Also, the camera and also the NPU kernel patches have been posted, so they'll be, I guess, introduced in the coming months. These things always have to be revised and some issues, amendments. Additionally, X2 support. So Qualcomm have already posted support for the X2 system on chip. And that's going to be 18 cores. Quite crazy. It'll also be optimized as well for desktop with a higher thermal envelope. So currently, I'm running Ubuntu 26.04, get a pretty good experience. I'm using this as my daily driver for the last 6 months. And I have some kernel patches applied to get additional power saving, but it works really nice. if you're thinking about considering like these laptops, the X1, which are now really, really cheap because there's now the X2 available, then you probably, if you're a developer, you might want to wait until, I mean, you might be okay right now, but then you might want to wait until a later version of Ubuntu later this year to then get a smoother experience. Just good to know. So what laptops currently have a support in Linux on the X1? So you can follow this link here. It points to the device trees in the upstream kernel, currently 6.19. Oh, sorry, 7.0, just recently released. You can see there's HP, Lenovo, Asus, HP again, Microsoft, different systems. The CRD is the Qualcomm compute reference device, so they kind of have that as like a something which all the vendors then reuse. And there's also the Windows Dev Kit as well, which they were selling for a while. Okay, this thing should work. Okay, so numbers. How efficient is it? Of course, I mentioned there's 12 cores there. They're full high-performance cores. So I ran a benchmark here. I think, does anyone have Linux booted here on the laptop? If so, could you just run one of these commands for me and then find some numbers? This stress ng, is anyone able to run that command? No? Okay. Okay, maybe. Okay, so one of our audience members ran this benchmark, and so the first command here is matrix1, which means single thread of execution, and the Bogo ops is 4.78 matrix operations per second. So that value on a Ryzen 7 4800 is 0.82. So the single core speed is nuts. It's really speedy chip actually. And then, okay, running across 12 cores, we get 33 almost operations a second. So it actually scales reasonably well, given it's a laptop, and it hasn't got like so many DRAM channels. I'll get some more. I'll get additional data for this later on, so that we have more information. Yeah, so that's actually impressive, given that it has such a like a small thermal envelope. So this is the NVIDIA Spark DGX. It's made by 7 different vendors like Dell and HP, and 128 gigs of memory. Like these other ARM systems, that DRAM is shared with the GPU. Okay, so it's very efficient. A key thing there is you can see it's a tiny computer that you can see by the size of the Ethernet socket there, 20 cores, and then it has this 200 gigabits networking, so you can chain them. So that's something which is already out this year and is kind of the future of maybe an AI developer using that. Like really next level performance. Okay, so yeah, in the future, look for the X2 on any design from all these other vendors. There'll be laptops from them, I suppose, and then in like 5 years or so, you'll have probably really, really good laptops with RISC-V cores. And then later on, if you want to see booting like a kernel upstream, then find me, and then we can compile and boot, and I can show you how it works. Any questions?
Yeah, thank you, Daniel. Thank you very much. Yeah, now we go into the QA time. One question. Yeah, okay, maybe. Thank you.
First, I would like to thank you for your talk. My question is, what hardware architecture differences caused the most headache when you were porting the kernel, and why?
I'd say it's not really so much differences in architecture. It's just that if someone else can't reproduce that, so if, like, say, there's a kernel crash and then someone like fixes it, then someone must have that system on chip or that kind of device tree where they can test that fix. And so because it's not a really popular thing, then, I mean, it is with Windows, but not Linux, then sometimes you'll find kernel issues which no one has seen because no one has this laptop.
Okay, thank you. I think we can still one more question. Yeah, thank you.
So when I last checked out the situation of ARM laptops, there was often a mismatch between the Windows ARM laptops and the Chromebook ARM laptops, where nearly the same chip would be used for Windows, but then it would use a different bootloader and completely different code base and would use ACPI, while in the Linux world you would use device trees, at least on the ARM platform. What is the strategy forward for at least Qualcomm or other Windows ARM laptops there?
Yeah, so I'd say that ACPI is what they used for Windows systems. And it does present some issues, of course, on Linux because all of their other work, like with the phones and everything, is pure device trees. It's actually easier in a certain way, I feel, with device trees. It's more logical and open. And I also thank Qualcomm for not using ACPI on this. But it is a headache, and so some of these are the issues. You actually have to disassemble some of these tables in ACPI from Windows in order to then figure out what's missing in the kernel device trees.
Okay. Okay, thank you. Thank you for the questions. Thank you, Daniel. Yeah.
Thank you, guys.
Yeah. And thank you to our speakers for the excellent presentation in the OS session. And next will be our database session. And thank you very much. Hope you enjoy FOSSASIA Summit.
He's going to share with us about the very interesting talk about the performance without magic, how open source database scale. So everyone, please give him a warm welcome.
Thanks, everybody. I hope you are prepared to enter the database world. We're just coming from hardware stuff, right? So now we're going to talk about database. Let me put my clock here because I used to talk too much. And I don't want to steal time from Sergey. That's going to be after me. OK. So as I said, my name is Charlie Batista. This talk is not about me. So, and the slide's going to be online, so you can later on take a look on my profile. Today we're going to talk about problems that might happen on the database world and how we can address those problems. So for example, who never heard that, well, this query is so fast last week, but now it's sluggish. The systems was working really fine yesterday, but now the user is complaining because they cannot even open the website, right? I think it's never happened in your life, right? So, and what happens when the database tends to be really, really fast, and then out of nowhere, it starts to be slow. And then you're going to complain with the developer, and the developer said, I didn't do anything, which is worse than when they say that works on my machine, right? Well, that's work on my device, that's work on my machine. That's the developer way. And also they say, I didn't do anything. And sometimes they didn't do anything, but the database is still sluggish, right? So today we're going to try to model, to have a mental model to troubleshoot those problems, to see what's happening with the database and what might cause the database to go so slow. And we're going to cover open source databases. So we're going to talk about MySQL and PostgreSQL, right? So, and this is the stack of we're going to talk today. So we're going to take a look on the application level, what things can go wrong on the application level, on the SQL and the query design, on the database configuration itself, also on the OS and kernel level. Sometimes we need to go deep down and troubleshoot. And we're going to take a look on the file system and close to the hardware, right? So I'm going to start with a low-level thing. And this is for all of us to be on the same page. That's very basic information. It's supposed to, okay, now it's better. So when you go for computer science on college, they're gonna teach you how memory is organized on a computer, right? If you see here down, we have this huge space here, which we call secondary storage. This is where your data lives when you save something on your database. That's going to be your SSD, your old school hard driver, your NVMe, your S3 on a cloud. That's your hard driver. That's your disk. That's the slow storage. So when things goes up, you have your main memory. That's what we usually when we call memory or RAM. That's when things are. So RAM is usually faster, is much faster than what we have down here on the secondary storage, right? So, and then we have, now we get into some specific area that are really, really fast, but tend to be very, very expensive. The first one is the cache. So the people that like to play games, when they buy a new computer, or they check for a new CPU, they're going to see how much cache memory that CPU has. And those people, they know that the more cache memory, the more expensive. And we're talking about kilobytes here, megabytes in some cases, but never gigabytes. So the more kilobytes you add to your cache memory, the more and more expensive that can get. And it gets really, really fast. And then we have the registers. The register is the CPU. So the thing is, the more information we store here, the slower the things can get. We go down the way, we get more space, but it gets slower. But why does it matter? Well, it matters for a few things. The first thing is, see the CPUs here on the top, and see the I/O controller here on the down. It means that your CPU doesn't have physical access to your hard driver. Every time that your CPU needs access something, it needs to ask for the memory controller to get the data. The data is pulled from the hard driver into memory, and then the CPU can access. Well, if you have a lot of memory, things can go really fast, right? Because memory is fast. Actually, memory is really slow. CPU doesn't work with the data in memory. CPU works with the data in cache and on the register. So every time that CPU needs to access the data in memory is slowing down a lot what the CPU is doing. But then we go even worse. So the way that we store data on the hard driver, they matter. If we store the data sequentially, we can access that data much faster. If we store the data randomly, that data is very slow. And what does that mean sequentially and randomly? Let's say we have the database, and my database, I have the table user. Well, I'm going to save user Charlie, and that information is going to be saved on the database. Let's say it's going to be saved on the block 1 here on my database. The database keeps working, and more information is added onto that database, let's say on the table orders, and then another user is inserted on my table Charlie, on my table user. Let's say that user now is inserted on the page number 7. So if I want to do a select that I get the Charlie and the user number 2, now we need to jump from one page to another page that's far away. So this is random access, because we're not getting the data physically one close to each other. And that's a problem. Well, on modern NVMEs, it's lesser than a problem. It was a lot worse on the spinning disks, but it's still lower, it's still a problem. And then we have the last thing that we're going to talk here to have everybody on the same page, what we call cache. So remember from the first picture, we have the cache here, the CPU cache. When I'm talking about cache, I'm talking about the CPU cache. So for the CPU to work well with the cache is organized on lines, what they call cache lines. Something like this. We have a big line. And each line has a specific size, what they call word size. So for a 64-bit CPU, the cache line is 64 bits. So it means that the CPU word is 64 bits. If we look at this code here, we have a problem. Anyone can tell me what's the problem in this code here? Yeah? The order.
I think some older systems, you put the lower memory variables at the end.
Why?
It'll only load it in 64-bit blocks or something, and you want to kind of make it so
Yeah, it's on the way, but yeah. The bool is 1 bit, but why is that a problem? Combining everything. Well, the order is a problem because remember the CPU size has a size, the cache line has a size. For the CPU to be optimized, it's going to try to put everything fit on that line. What happens if it doesn't fit? In this example here, on my 64-bit CPU, an integer is of 4 bytes. A bool is of 1 byte. So we have 4 bytes, 1 byte, 4 bytes, and 1 byte. So going to be 5 plus 5, 10 bytes. So theoretically, this is more or less how I organize, right? The problem is, it doesn't fit. Because it cannot do here 8 bytes together, and there is this bool in the between, it's going to have a huge space until to the next one. This is what we call padding. And that's why we align all the 4 bytes together, all the 8 bytes together, so we make it more cache friendly for the CPU. And why does it matter? We'll see later on. Another thing, the last one before we really get into stuff, is file organization. That matters because your database is divided in different files organization, right? So MySQL, for example, it's usually extensively B3 file organization. So when you create a primary key on MySQL, the table going to be organized by the primary key. The order of the table is literally the order of the primary key. So every time that you do a select using a primary key, that's the most efficient way to search on a MySQL InnoDB table. On Postgres, for the other hand, it doesn't use it. It uses a heap file organization. And a heap file organization is just put one block after another. And it doesn't care. So fill one block, put another one. Oh, what if I update? The update is going to get the data from where it was before and append at the end. And that's it. So there is no physical order on a PostgreSQL table. So all PostgreSQL tables and indexes, all indexes, they are secondary indexes. They are not primary indexes. Even the primary index that you create on Postgres is just a naming for an index that is unique on your table. But still a secondary index. Even the primary index is a secondary index on PostgreSQL. Why does it matter? It matters because every time that you do a select using an index, it needs to find the data on the index first, and then go to the table and to fetch the data. So the thing that was supposed to be I just forgot the name, a sequential access, sorry about that. Now it became a random access because all the B trees, they are random for nature. And that's a problem. But now that we understand, yep. Well, they work similar, they work the same. So they're just the tree. Every time that you insert something, they need to find the position, organize the tree, make the rotation for the tree, insert that data, and that's it. So there is a nice thing on PostgreSQL that they call hot update. So on the database, they work in pages, right? So we have a page that the data is filling when we insert the data. So on PostgreSQL, the data is, if I'm not mistaken, 8 kilobytes page. So if you create a table, it was a 25 minutes presentation, no? Yeah, because they're saying missing 2 minutes. Yeah. Okay. Yeah, because I just saw 2 minutes left if we just started. So we work in pages. The thing is, every time that you update on PostgreSQL, it does not do an in-place update. It gets the data, it changes the data in memory, and then it saves back inside of the table. And it's going to save elsewhere, like at the end of the table. If the page has a space for that one, it's going to save on the same page. Your index on PostgreSQL holds the address of that page. It does not hold the physical address inside of the page. So if you still has a space inside of the page, you don't need to change the index. Yeah, to insert the real data on the index, you are updating the table. You don't just update the index without changing the table. I think I get what you meant. We're going to get there. Okay. So the first line of defense for performance is the indexing. And why is indexing important? Well, indexing is important because the way things are searched. So, for example, a very naive index implementation would be a B tree implementation where we have a split of 2. So that a log of 2 performance. But what does log of 2 performance it means? Does anybody here really know what log means? Because logs usually, this is something weird to understand, right? So a log, what is a log? What log of 2 means? Well, yeah, we're trading multiplication to sum, right? For example, what is the log 2 of 100? It's 10. What's the number? A power of 2, that is 100. So using this way, instead of doing a full table scan, like where you need to search for 100 values, using a B index, you can just search on 2 different values. So this is the power of the index. Database, they use a more advanced technique with a B+, which use another type of logs. It's exponential. It's a smaller. It's a larger one, so it's much faster. But the thing is, index, they are not free. Every time that you create an index and you need to insert, update, or delete, you need to update or delete that index as well. So index can improve a lot of the performance when you're doing a search, but it's a problem when you're updating the tables, right? So there are some index patterns that help. One is what you asked, what is the covering indexes? So what is the covering index is when you save all the data that you need to retrieve on a select inside of the index itself. For example, the user table, every time that you do a login, you need to get the username and the password. If you get an index that has your username and password, and you do a select, you only go to the index. You don't need to go to the table. The problem is, your developer is probably doing a select star. If he's doing a select star, you don't have that star in the index. Star means all the columns. So your optimization is gone. Now, just to do a login, that the only thing that he needs to validate in the beginning is the username and password, and then he can lazily fetch the data if the username and password is correct. Now we are doing an index search and then going to the table to get all the data. Your optimization is gone. That's one of the problems why you say to the developers, don't use a star if you only need 2 columns, because those 2 columns may be a covering index. So another thing that impacts a lot is memory. How is memory used on your database? So we always try to cache things. And the first layer of cache is memory, is RAM. So the databases, they use RAM differently. MySQL, they have their own implementation of buffer pool that's highly efficient. And we always try to use the more memory for the buffer pool as we can instead of PostgreSQL. PostgreSQL relies a lot on the OS cache. So we don't give that much memory to the database itself because a lot of the data is going to be on the OS cache. We don't want to have the same data on 2 different caches. So for MySQL, you're going to give a lot more memory to the database than the PostgreSQL itself. There are some parameters here. Those are some basic math, just basic recommendation. Obviously depends on your database, on your case. But like as a rule of thumb, usually 80% of RAM for MySQL, depends on the amount of RAM that you have. If you have 1.5 terabytes, you can give more than 80%. Because, well, your OS doesn't need 200 terabytes memory there, right? So you can give more to the database. And the same for PostgreSQL. If you have that amount of RAM, maybe 25% of memory is already too much. So depends on your case. And the work mem trap. So database, they have one area to work that they also allocate memory. And what is the trap? Some of those areas, for example, the work mem, they use pre-connection, and some of them, they use pre-join. If you have one select that has 20 joins on that select, you might be using 20 work mems for that select. Or not necessarily 20 work mem, but a space that's gonna fill for all of those selects. And if you have 1,000 connections that use, let's say, 1 megabyte RAM for this guy, in 1,000 connections, you can do the math. So you're probably gonna get an OMQ on your database. That's a problem. I/O, this is where the database dies. So this is when they come to die. Remember that we talked about random I/O. So it's a problem. I/O is really, really slow. And one thing that we have a lot is latency. What is latency, by the way? Latency is the perception that you have when things get slow. Why I say perception? Because sometimes your database is really fast, but your page loads really slow. So the time that we wait for the data to go and come back is latency. Latency can be caused by I/O, can be caused by the network, can be caused by the CPU. And usually, I/O and network are major problems. And what happens when you go to the kernel itself? Well, there are some parameters that really matter. One of them is that swappiness. In the database, people, they tend to not use swap. A lot of people tell you, if you go to the internet, they say, disable swap on your database. That's one of the worst things that you can do for your database. Because you want your database to slow down, but you don't want the kernel killing your database because you don't have memory. So if your database is really badly optimized, and you are going to swap, it means that the database is going to be really slowed down. The user is going to call you and say, the database is really slow. It's going to give you time for there, figure out what's the problem, or in the worst case, stop the database or the application before the kernel itself kills your database because you run out of memory. Swappiness equals 1 means only use swap when it's extremely necessary. There's no more option, no more memory left. Now you can come to swap. That's the safer way. There's another thing here, which is this transparent huge page. Well, for user applications like or your laptop, that's fine. That's usually pretty good. For database, this is really, really bad. Because that can fool the kernel and kill your database in the best case scenario. And in the worst case scenario, that's going to give you a lot of memory defragmentation and slow down your database a lot. So that's a huge problem. I/O scheduler, another thing. So on your database, you need to check what is the scheduler you're using. If you're using NVMe disks or SSD, you probably can get a lot of optimization boost just changing the scheduler for your. And connections, folks, they are not free. Every time that your developer comes to you and asks, oh, I need more 5,000 connections to the database because the application is really slow. Guess what? Let's say you have 1.5 terabytes memory, and you have 200 CPUs. So if you give 5,000 connections, it means 200 divided by, it's 10 connections for CPU, right? One single core can only do one thing at the time. It means context switching. The CPU needs to, every time that gets another connection, stop what it's doing and split the time. So instead of making things faster, that's going to slow down your database. And those are some myths that we're talking about. More connections, more RAM, more things going to boost your performance. That's not true. And read the query plan. So we had a customer that they had, I mentioned 1.5 terabytes memory because this customer, they had their database fully memory. They had 1.5 terabytes memory on the hardware, and their database, it was less than 1.5 terabytes. And it was super slow because their queries were really badly optimized. After doing some optimization, some schema changes, we could save them half of the cost. So instead of 1.5 terabytes, the setup for each database was around 500 gigabytes memory, and the performance were around 7 times of the performance that they had before. So more hardware does not mean faster database. We're getting to the end, so keep your statistics always up to date. Remember the problem that the developer said, well, it was so fast until yesterday. What's the problem? Well, maybe the problem is your statistics until yesterday was super accurate, and after that last update, it shifted. The distribution of the data in your table shift, and now your index just does not work anymore as it was working before. And it's getting things really, really slow, right? So those are some software tunings that we can do. We've seen a few of them already. I'm running because the guys are shouting at me again after 2 minutes, you know. And now looks like it's 2 minutes, and Sergey already here as well, so I don't want to steal. So those are some things that you can do. And remember, yeah, that means timeout. Let's go to the key takeaways here. Folks, when you increase hardware and you add things, you can increase performance 2, 3, max, let's say 5 times. When you do a database optimization, sometimes doing a reordering of your database, you can improve performance by order of magnitude. Like the example that I gave, you could improve performance by 10, 20, sometimes even more times, just doing a good database optimization. Well, I hope you enjoyed, and thank you. And questions, if we have time?
Yeah, thank you so much, Charlie. We run out of the time a little bit, so we don't have enough time for questions, but please feel free to reach out to him later. Outside of the talk, I believe like he will very happy to answer all of the questions you have. We can have a short break for like 3 minutes for us to set up the next presentations. So we will start again in 3 p.m. In the meantime, like Hi everyone. Hopefully you guys are already ready for the next sessions. So please welcome Sergey. He's the founder of Solanica, and he's gonna to bring a very amazing talk, a next amazing talk for us about how community-driven platform enable the next generation of data. Please give him a warm welcome.
Hello everyone. Thank you. So 6 years ago, I joined the company called Percona, and I started working on running databases on Kubernetes. And I had hair back then. Now I don't. So, and now I'm working in a company called Solanica. I founded it, and we continue running database on Kubernetes because I like to suffer, but I don't want anybody else to suffer with running databases on Kubernetes. So today my talk is all about that, and I'll say word Kubernetes too much, so sorry for that. So when you run databases, there are usually 3 doors that you can open. The first door is, I call it legacy. Maybe for some it's not really legacy. It's when your developer needs a database, the ticket is created, and then some scripts are executed. It can be infra as a code, it can be some custom shell scripts, and so on. Then there are managed services from various public clouds, and then there is the third door is cloud native. And there are no good doors or bad doors. I like to think about these doors as marriage. Sometimes you open this door and it ends up with a complete disaster for you, but sometimes you find the love of your life and you live happily ever after, right? So for everyone, it's a choice, right? And for managed services, I like to pick on those a lot. But when you run your databases in the clouds, there are usually some traps that you should be aware of. And the first one is obviously a cloud tax. It's usually 3 to 5 times more expensive than running it yourself. Even in the cloud, if you run on EC2 instances, it's going to be 3 times more expensive for you to run a service like Aurora or RDS. Hidden costs is another cloud tax, is when you have IOPS. Nobody tells you about Amazon Aurora IOPS usage and how fast it can bring your cloud bill up, right, and kill your wallet. Underutilization is the usual problem when you have a database that needs to accommodate your load during peak hours. What you do, you usually run a bigger database. You can run something like Amazon Aurora serverless, but they don't scale that fast, and they come also with additional price tag and with other issues that, well, who knows what can happen. Compliance and sovereignty is another problem, especially now in this geopolitical situations where you want to be sure that your data resides in the legal entity that your government approves on, and that you also have full control of this data. And no matter where it runs, the clouds usually can't promise that your data is there, right? Feature lag is another thing. It's not that usual, but you can see it as well a lot in, for example, for Postgres on Amazon, that you don't have specific extensions. And you need to ask Amazon to add it, and it takes usually a few months or even years sometimes in different cases. And the usual unifier for running any workloads today anywhere is Kubernetes. So for those who are, for some reason, who is familiar with Kubernetes, who knows what it is? Okay, okay, I was expecting more hands, but okay. So what Kubernetes does is just an orchestrator for your containers. So you have Docker containers or any other containers, and what it does, it just helps you to put them on correct nodes and run them, and it automates a lot of work for you, so you don't need to think about how to move one container from one node to another, how to create a load balancer, and so on. It just does it for you. And Kubernetes today can run almost anything. It can run applications, it can run databases, and as Kubernetes is kind of universal, it also brings you freedom of running your workloads anywhere. So you can run it in the cloud, you can run it on-prem, and you can migrate from one place to another relatively easily. And as for cost savings, Kubernetes also comes with nice ecosystem that has different pod autoscalers, so it can reduce and increase your CPU and memory usage on the fly. So you don't need to do it manually. It's going to be fully automated, and you don't have this over or underutilization problem. And there is a myth that, well, you should not be using Kubernetes for data. And that's a good one, because Kubernetes originally was created for stateless workloads, meaning that no data should be there, because all containers, all pods are immutable. So it means that you can't change really them. They just restart and are recreated from the point where they were built, right? But a lot have changed since like even 6 years ago when I get completely bold. And now when you think about running databases or any stateful workloads in Kubernetes, the usual answer is operators. What Kubernetes operators is, we'll talk about it more on the next slide, but I just want you to be sure that when people say it's too complex to run data on Kubernetes, it's not. The answer here is just use operators. It's going to automate all the pains for you. When they say, well, stateful is scary, it's just for stateless, well, it's also wrong, because you can use operators, you can use persistent volume claims, and so on. So you decouple compute from storage. And another popular thing is that now some of you might be DevOps engineers or SREs, and you treat your applications as cattle, not pets, which means that you can easily restore one application container, one application node, and it's not going to affect the whole service. And the same goes for databases when you run them on Kubernetes now, because you can start treating your databases as cattle, not as single pets. So if we look into operators more, what they do in a simple term is that on the left you have what you write. So you just send to Kubernetes API some specific YAML manifest. It says, I need a Postgres cluster, I need this number of nodes, I need this storage, I need this extension, and yada, 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 all the configuration parameters. And what operator does for you, it just provisions all the necessary resources, all the configurations for Postgres, and you don't need to know how it actually works, because operators have this encoded wisdom in them. They configure the replication, the backups, the security, all the encryptions, everything. So you just throw some YAML manifest at Kubernetes API, and as a result, you get a working database, and you don't even know how it works. It just works. You get the endpoint to connect to you. And so CRD, custom resource definition, is your intent or desire. So I want Postgres database with replication. I want Mongo sharded database across different data centers. And what operator does is just says, OK, I'm going to do it for you. And this is the endpoint that you should connect to and run your database. What we're working on in Salonika is we're trying to make things even simpler, because all the operators out there for databases, they're different. They have different YAML manifests, they have different structure, they have different integrations, and you still need to learn Kubernetes, you still need to understand some concepts of it. What we're doing, we created a product, it's fully open source, called OpenEverest. And what it does, it allows you to have a web UI or an API to deploy and manage databases at scale with ease on any Kubernetes environment. You can integrate through CLI as well. You can integrate through CRDs, custom resource definitions, directly. And we support MySQL, Mongo, and Postgres, but also adding ClickHouse, Redis, Milvus, and whatnot, because we have a request in our roadmap for different other technologies. And the real beauty of cloud native is its ecosystem. So on this picture, you see all the projects in cloud native ecosystem today. You can't even see what it is, but it's like more than a couple of hundred today. And you can easily integrate with any of those, with OpenEverest and with any other workloads that you run in Kubernetes. For example, if you want to scale automatically your workloads, you integrate with horizontal pod autoscaler or KEDA that allows you to add more nodes on the fly. If you need to scale up, you can integrate with vertical pod autoscaler, monitoring tools, everything is there for security, for anything. And you can integrate easily. That's the beauty. Open Everest use cases are different, but not that different. So the first most common use case is that you're building your own private DBaaS. It can be on-prem, it can be in cloud, doesn't matter. But if you have a developer that needs databases daily, you can give them the web UI or API to use, and they can just click and the database is going to be deployed following the rules that you defined before that. Internal dev platform is kind of similar, but it allows you a lower level integration. You can integrate with custom resource definitions directly or with Kubernetes API directly, so that it depends on, like, Backstage is a good example. You can integrate with Open Everest, and you can forget about running and managing databases forever. Sovereign cloud, as Open Everest runs anywhere in any Kubernetes environment, you can run it locally, you can run it in your own data center. You always know that your data is in this data center, it never leaves it, so you have full control over your data. And cloud ready, I like this term, is a lot of companies are now saying, okay, we don't want to run in Amazon, but we want to be ready to migrate our workloads to Amazon at any time or to any other cloud. And what they can do is they can run everything in Kubernetes, and then it's just lift and shift to another Kubernetes cluster without changing their application, without changing the deployment pipeline. It's just a straightforward process. So your whole stack becomes cloud ready right away. So as for the roadmap, everything that you see on this screen now is already happening. So our roadmap is 100% public. You can look at in GitHub. What we're working on is now on modular core, which would allow you to add more and more plugins, more technologies, more integrations with ease. And that's where we see a lot of magic happening with the community. That's where the most traction is happening. Nobody wants to contribute code to your core. They want to build plugins with you and so on, which is a good thing. We're already fully open source, but we are donating the project to CNCF. So we applied to CNCF Sandbox. It's under review. Hopefully it's going to be reviewed tomorrow, March 10th. So we'll see. And yeah, integration, I told you about this already. We can integrate with any cloud native tool, and we have a bunch of blog posts about it. You can have a look at our website. Before I finished, I wanted to say that tomorrow, no, not tomorrow, March 11th, day after tomorrow, there is a Percona University event. It's completely free. Anyone can come and join, so look at the website or scan the QR code to learn more. There will be a lot of database practitioners, folks from other companies who are going to speak there, so feel free to join. And as for Open Everest, join our community. We're open source. We welcome everyone in our Slack, in GitHub, and yeah, come by our Salonika booth and you can get a chance to win a drone. Thank you, everyone, and I hope you're not going to get bold. Cheers.
Yeah, thank you so much, Sergey. All right. Yes, very, very quick questions.
So how about the availability features which normally RDS gives us, like automatic failovers, and in case there's an update in a Kubernetes worker node, how about the availability?
Yeah, so we rely on various production tested Kubernetes operators, and these operators, they already come with encoded high availability, with replication and so on. So when you deploy a cluster in Open Everest, what you get is a highly available cluster with load balancing, with security configuration, everything. So you don't need to think about it.
Thank you so much, Sergey.
Thank you.
Yeah, we're going to move into the next session now. Can I ask the speaker? All right. Hi, everyone. Please welcome to our next speaker. Now we have Kushi Shah. She is a senior software engineer at McKinsey Combine. She loves working with data, and she's going to bring a session about how Spark execute your code, a radical mental model. So please give her a warm welcome.
Hey, thanks for the introduction. Good afternoon, everyone. I'll just be talking about how Spark executes your code. Anyone here have worked with Spark before or have heard of Spark? Okay. Right. Okay, so for many people who are just like beginning out with Spark, they might feel that Spark is extremely confusing. So if you work with just normal languages like Python, you might think that after like every line you run, you would see the output, but that is not the case with Spark. So in Spark, nothing seems to happen when you expect it to run. And then sometimes you might think that the job is taking too long to run and you wouldn't know why that happens. So before I get into the details of why, I would first just like to go through the architecture. So Spark is a distributed computing engine, and it follows the master-slave architecture, where the driver program is the master node, and then you will have all the slave workers as all the slave nodes as the worker nodes. And over here, basically, the driver program is where your Spark application gets submitted to. So your driver program is the one which has the full context of your code, and it would like schedule the work across the different worker nodes. And the worker nodes basically don't have an idea of the code, they just execute what the driver sends it. So in each worker node, you could have many executors, which are basically JVM processes. And each, and the worker nodes, and all of the clusters get managed by the cluster manager. So this is just a small intro to the architecture so that the rest of the slides don't feel very woozy. So yeah, coming back to how Spark executes is that Spark doesn't execute everything line by line. It would first build a plan, and then it would find the best way to execute the code and not just like directly run repeated codes. So what Spark follows is a lazy evaluation where it delays the execution intentionally. So this would allow Spark to optimize its entire job and then remove any redundant operations, and then just combine it all so that you have the optimal plan which runs efficiently on your clusters. So the lazy evaluation exists because Spark wants to see the full plan. So I'll be referring to this example in the rest of the slides. This example is basically you have the sales table and the customers table with the following columns: customer ID, your revenue for the sales table, and the customer ID and the region for the customers table. And you go through a few transformations, transformation functions, which is basically filtering the sales on the year, and then just joining both the tables on the customer ID. And you finally want to sum up the revenue per region. So you would wonder now that when does Spark actually start executing this code? So in Spark, you have two transformations. I've listed a few examples here, like group by, join, distinct, order by, repartitioning. And then there are another set of operations called actions. And these are the ones which actually trigger, ask Spark for results and it will trigger the execution. So for example, you want to write the data frame as a Parquet file, or you want to store it as a CSV, or you want to get a count of all the data, or you just want to like display the result. So whenever Spark encounters an action, it would trigger execution. So whenever, so in your Spark application, you might have like a few actions, and whenever you see that an action is triggered, a job is created. So a Spark application can have many jobs. Below is just the diagram, a flowchart of how Spark executes it. I found it on Databricks. So this part is just basically how it finds the optimal plan. It does not yet start executing the code. So you might have your initial data frames, or you would have an SQL query. So first, Spark would check your query or the data frame to see if it's syntactically correct. And once it sees that it is fine, it would create an unresolved logical plan. And then Spark has an internal tool called a catalog, which basically lists all the tables which are present, all the columns present in the tables, and what the data types of all the columns are. So Spark, from the unresolved logical plan, Spark would see that the stuff you have in your query matches with what's in the catalog. And then if there's some issue like with the semantics or anything, it will throw an error. But otherwise, it will create a logical plan. And once you have the logical plan, Spark would run a few optimizations on it. So for example, an optimization could be something like if you have, say, 10 lines of code and you're filtering after a few operations, but if Spark thinks that that filter can be applied at the source level, it's going to do that so that you don't carry the whole like data frame and pass it through all the steps. But like if you move the filter down to the data source level, you just need to work on the particular subset of rows. So this is one such optimization. Spark runs many optimizations, and it would create an optimized logical plan. And from that optimized logical plan, Spark would create many physical plans, which it then runs through a cost model, and then it would select an optimal physical plan. And then it would move on to, actually executing the plan. So till now, everything was just planning, and now is when the execution begins. So now Spark has an optimal plan it can work on. So it will first create a DAG, which is basically a directed acyclic graph. So that would represent the full execution plan of a job, and then it is built by the driver. So now a DAG is divided into multiple stages. So you might wonder how many stages does a DAG divide the work into. So this is based on the number of Y transformations you have. So referring back to the kinds of operations, we had two, transformations and actions. And under transformations, we have, again, two kinds of transformations. One is basically Y transformation, and other is narrow transformations. Y transformations are the one where you would shuffle the data across the network so that it reaches the other executors. And narrow transformations are the ones where you would just run the data in that particular executor, and you do not need the data from any other executors. So example of Y transformations are something like doing a group by or a join. And examples of narrow transformation is something like filter or select or just a count. And so basically, whenever it starts reading the DAG, whenever Spark encounters a Y transformation, it breaks it down into a stage. So basically, everything, all the narrow transformations would fall, would be in a particular stage, and whenever it encounters a Y transformation, it will break into a new stage, and then it will run the subsequent narrow transformations. And then if it again encounters a Y transformation, it's going to break into a different stage. So now each stage gets divided into multiple tasks. So in Spark, your data is partitioned into different partitions. It's divided into different partitions. And what a stage does is it'll create the number of tasks as there are the number of partitions. So for example, if your data is divided into 20 partitions, then your stage will be divided into 20 tasks, such that each task would process each partition, and each task would run on a particular executor core. Moving on. So we discussed about shuffles, which is basically you're transferring the data across the network so that other executors can access the same data. So shuffles are an expensive operation, and it would usually make your Spark applications slow. So what exactly happens during a shuffle? So for example, if we take a look at the same example we had, it's the one here listed below. If you just pick the line where we are grouping by one region and taking the sum, in this case, like going back, over here first, what happens is on every executor, you'll have some data. So in that particular executor, first, Spark would run that transformation, the group by, and then it would store that intermediate result on the disk. And this data is transferred across the network to the other executors, such that all the similar keys would land on the same executor. And then finally, the executors would read all the shuffle data from the disk, and then it would run the final group by to get the output. So why this is slow is because Spark usually runs everything in memory, but whenever disk operations are involved, things become slow because they are naturally slower than the memory operations. And then since there is also network transfer, there's also those latency and bandwidth limits. And then large data movement would increase the memory pressure on the executors. So hence, shuffles are an expensive operation. So I'll come back to the slide. I'll talk more on the common reasons or like the things you need to check first to see why your Spark jobs are slow. So first, as we had discussed, was shuffles in the previous slide. So if you have a lot of shuffle operations, your job can become slow as it has to move the data across the network a lot. So again, the disk operations are going to take time, and then there could be latency issues. Second thing is if you have data skew, which is basically if one of the partitions has a lot of data compared to the other partitions. In such cases, the stage cannot complete until the longer partition fully executes the job. So what happens here is that there's the stage is like on pause, not on pause, it's working, but like you can't complete the stage until all the tasks are completed for a particular stage. So the next reason could be is because if you have fewer partitions than you have the number of executor cores. So in this case, suppose you have 10 executor cores, but then you have 5 partitions. So what's going to happen is the remaining 5 executor cores are going to remain underutilized, and all the work would be done just by the other 5 executor cores. So there is resource underutilization. And then another case could be there are very small partitions, but then there are a lot of partitions. So you could have like, say, 1 MB partitions, but then you have like 150 of them or 200 of them. So in that case, there's a lot of task scheduling overhead. So these are the common reasons, and Spark jobs could become slow. These could be a good place to start looking at start looking for issues. Coming back, when I was mentioning the plan, I had mentioned the physical plan. I thought I'll give an example of what the physical plan looks like. You can view the plan with the explain function, which is mentioned on top. So we are using the same example. Over here, we always do the physical plan from bottom up. So in this case, if you have, we have 2 tables, sales and customer, and then we are filtering the sales table on the year, and then we are joining it with the customers table. So in over here, the last 4 lines, which is basically the sort, exchange, filter, and scan, those are run for the customer table. So whenever you see the keyword exchange in the physical plan, that means a shuffle is happening, which is basically expensive. So if we just like scan through from bottom to top, first it scans the existing RDD, which is basically it reads the customer table. And then Spark itself has added an optimization of is not null. And then you do an exchange, which is basically shuffle. Over here, the partitioning scheme they've used is hash partitioning, which is basically you get the hash function and for all the keys, and then wherever, over here in this case, the customer ID. And then the similar customer IDs would go to the same executor, and then you sort it there. Now the same thing happens for the sales table too, which is the 5th line from the bottom till the sort line you say. So it will again read the sales table. It's gonna, Spark adds its own filter of is not null. And then it also checks if the year is 2024, which is already present in our query. And then it also has another function, another filter of is not null on customer ID. After that, it again shuffles the data so that all the similar key, over here the customer ID, all the similar customer IDs would belong to the same executor. And then it'll again sort it. And then it'll finally merge both both the tables. So the sort merge join is basically where the sorting happens, where the join happens. And then if you look up a few lines, you have hash aggregate and exchange, and then again an hash aggregate. So if you check the example, the group by line you see, line 5, the group by on region and then sum the revenue, that is what's happening there. So we first do an hash aggregate on the region, on the local executor, so that whatever is currently there, it gets, you get the group by and the sum of the revenue there. And then this output, this intermediate output is being shuffled across the executors. So that is the exchange hash partitioning line you see. And then this, and then this is then, again, you run a hash aggregate, which is like the topmost line, which basically does the final group by and then sums up the revenue. And then the action result.show is what actually triggered the execution. So yeah, this is pretty much what I wanted to cover here. So just summarizing this, whenever in the code Spark encounters an action operation, which is basically a show or writing a file as a parquet or anything, that is when Spark will actually start executing the code. And then it will first create a plan and then divide the plan into DAG. Get the DAG from the plan, and then it'll divide the DAG into different stages based on the number of wide operations it has. And then it'll divide the stage further into many tasks depending on the number of partitions the data is divided into. So this is what Spark execution looks like. And yeah, if you have any questions, thank you. Please feel free to reach out. Yeah.
Yeah, thank you so much, Kushi. I will give the mic to the person who raised hand first.
Hi. So my question is about the optimizer and this physical plan. So you use the analogy of a chef and recipes.
Yes.
So my question is, when you look at the recipe and you find that the optimizer has made a less than optimal choice or a choice that you disagree with, how do you decide when to trust the plan versus override it?
So a cost model is generated by Spark, usually which would find the most optimal way of doing it. And again, there's this thing called adaptive query execution, which has come out in Spark 3, which basically Spark itself would decide like which query is optimized. But then always, if you find something wrong in the plan, and you can actually look at the Spark UI to see which which jobs take too long to run. You get all the metrics there on the Spark UI. So if you still feel like something is not right, you can go edit it in the code yourself, as in like you can repartition it or do steps like that so that you can like get your code running optimally. Yeah,
Yes.
I hope that answers your question. Yeah.
Yeah, all right, thank you so much.
Yeah, so there are also a few configurations you can set, like say default partitions and things like that. I feel like we can talk about it more later if you want. Yeah.
All right, thank you so much, Kushi. Actually, we will start the rec now. So if you guys have any question more for our speaker, please feel free to see her after the presentation today. So we're going to have the coffee and tea break, which happen now. Everyone, please welcome to stand up, go out and grab a coffee and talk to people. Please go back into the next 15 minutes in 3:50. We will have the next talk happen in 3:50. Thanks, everyone.
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption, we do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption, we do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, like, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells
I love you so much.
earlier than ever before and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
The future can feel impossible, but we build it together, one beat at a time. We start with technology that helps us to do impossible things. Things like detect cancer cells, I love you so much, earlier than ever before, and defy expectations around the world. ARM is in billions of devices around the world, unleashing the power of AI, helping us to do the impossible, because impossible is just technology waiting to happen.
Now, and as a father myself, I have two sons. One is 16, one is 9, and I see how they interact with the internet at large, with social media, with messaging apps, and now of course with AI. And it's hard not to see the benefits and the importance of having some sort of protections in there. On the one hand, we do want end-to-end encryption. We do want that privacy. On the other hand of the scale, of course, where there's no encryption and anyone can see those messages, and that's not something that we want either. So the challenge really is figuring out, is there a middle ground? And if there is, how do we reach it?
Hi everyone. I think hopefully you guys already enjoyed the break and have some time to recharge energy. We're going to start the next section now. Please welcome to our next speaker, Shamir. He's going to share with us about the reactive notebook for modern data work. So please give him a warm welcome. It's your stage now.
Hi everyone, I'm Shamir. I'm a software engineer at CoreWeave. Okay, great. So I think notebooks are awesome. You may have different feelings about it, but they let you mix code, markdown, and create visuals all in the same place. And because of that, you can see your data while you work with it, creating this iterative development experience that's unmatched in any other editor. And it's not just me. There's over 10 million Jupyter notebooks on GitHub. And these examples are like cutting-edge research on GPT transformers, black hole research, and audio-visual analysis. It's used all the way from academia even to production for some companies like Netflix. However, not everyone shares this feeling. I scoured social media, and these are like the reputation for notebooks. Like people say it sucks, you can't use it in production, it's only like a playground. And it's so bad that we have 2 other events or talks during this event that talk about how notebooks are like bad and how we should fix them. So what's the problem with notebooks? There are a few. One is there's hidden state. In this example, I have 2 cells, x is 1 and x, the output of x is 0, and they reflect 2 different like states in your application. This is because the second cell hasn't been rerun yet. And if I delete the first cell, x still holds a value. So these are simple snippets, but if you create a large notebook where you have multiple definitions of x and some cells are mutating x, who knows what the program would actually run when you share it with someone else. So it creates a lot of reproducibility issues. It's also not very maintainable. So this is for Python notebooks. I'll talk a little bit about other languages, but Python notebooks are stored in IPYNB format, not a Python file. So you end up with Git diffs like this. And you try to version control and apply like good Python practices, it's really difficult. It's also not very reproducible. So what ends up in production with data scientists is they come up with like 10 notebooks, all named untitled, and it's very difficult to code share, like create reusable functions, and apply like good software practices. So with that in mind, could we create or reimagine how notebooks are created? Could we make it reproducible so the code on the page matches the outputs that you see? Can you make it maintainable like any other software and apply the best practices of engineering? And can we make it productionizable, executed as a script, deployed as a web app? From there was born Marimo. It's a reactive Python notebook that's open source with a lot of batteries built in. Akshay, who created Marimo, was doing his PhD in Stanford, and he ran into a lot of problems with Jupyter, so he created this. And I've been working on Marimo, the open source, for about 1 year now. So firstly, unpacking what a reactive notebook means. Traditional notebooks have a mutable workspace and an arbitrary cell execution order. So if you rearrange your cells, it may behave differently. And the execution history influences the state of your application. So I could run my Jupyter notebook in one way. If I share it with another person, it may run totally differently. So it's not, the outputs may not be reproducible. So to fix this, let's eliminate execution history. This isn't a new concept. So Excel does it as well. If I define one cell at the top and all my subsequent cells refer to it, when the original cell changes, everything else changes as well. So there's like a single source of truth. Applying this to a notebook, I have 3 cells here, like x, y, and x plus y. If I change the first cell from 0 to 1, you would notice that the last cell, x plus y, the result changes to 2. And that's it. A link is created between the cells. So it recalculates based on your cell, like based on the definitions of the cell. Naturally, there are some constraints that need to apply because so if I deleted x here, we throw an error to the user that your notebook has something wrong with it. X is no longer defined, and you need to fix it. Oh, okay. So taking the step further, I could add a UI element like a slider, move it around, and it affects the markdown cell at the bottom. then taking this to a more complex application, there are two cells here. One is a chart cell, and another one displays the values of the selection. So the chart is actually showing a diagram of handwritten digits. So if you notice, like the orange color is the number 1. So they are all grouped together. And if I want to inspect my data on the chart, I can create a selection. It returns back Python values that feeds into the second cell, and I can transform that values, which are like numerical digits, and create images. This is the code snippet for it. It's a bit small, but so at the top, I create a selection, I get back the value, I pass it into the last cell, and I can visualize the images. This is another sample. This is, I don't know if you know Dan Brown, or 3 blue, 1 brown. He has this famous like seam carving example, and it utilizes the same concept. So under the hood, how it works, we create a DAG based on the cells. We statically analyze your Python code, and each cell would have definitions and references. So if another cell has references to like cell A, we create an edge between them. So it will look something like this, where you define A, and then B and C, who refer to it, would update if A updates. It's also a pure Python file format, so you don't need to create a custom file format. You can apply rough and other linting tools that are familiar to Python users. It will look something like this. So the first one is a markdown cell. So you can easily use with Git, and you can execute it as a Python script, like Python run, notebook. So this isn't unique to just Python. These are 2 examples in the different languages. Pluto is for the Julia programming language, and Observable is for JavaScript. It looks something like this. So if you're interested in other forms of reactive notebooks, you can consider those. To talk about databases, so Marimo supports DuckDB by default. I love DuckDB. So this is an in-memory engine. DuckDB can also connect to the cloud, but you can by default run DuckDB, and you can read like CSV, S3, Parquet, and you can create your transformations based on that. This is a more complex example using ClickHouse. I just created a connection to ClickHouse, create an SQL cell, read from S3, and I get to view the data from S3. And on the left, you see like a schema explorer. So you can inspect like what tables and views you have in your data. So let's introduce reactivity to this workflow with data, right? Here I create a drop-down of pickup locations. This is based on a taxi dataset. And the value of that drop-down feeds into the SQL query. And the result of that SQL query feeds into a chart. So what I end up is with an application like this. So this is app view, where I hide all the code, and I can like just share this, like create a link that I can share with end users. And they can like play around with this dashboard or like application, change the drop-down value, and they can inspect the table and the chart. Okay, don't know how much time I have, but to wrap up, if you'd like to check us out, and you can go on GitHub, and there's also Molab, which is a form of Google Colab, but from Marimo notebooks. You can try it out. It also works in the browser, so you can use WebAssembly. Feel free to check us out, and if you want to connect with me, my page is down there. Here's the team, if you're interested, and that's all. Thank you.
Yeah. Thank you so much. That's really awesome, Shamir. We have like 5 minutes for the Q&A and wait for the next talk. So anyone have any question for our speaker? All right. Yeah.
Only supports Python. Yes.
Yes, Marimo only supports Python for now.
All right. Please feel free to continue to reach out to Shamir after the talk. Do you have a question for him? All right. Yeah, that's perfect. Thank you so much for the sharing today. We will move into the next session very shortly. Yes. All right. Hi, everyone. We will move into the next talk now. So please welcome Shora. He is the developer relational engineer at IBM, and he's going to share with us about RESTO in the real world, fast, federate, and code-efficient analytics for modern data platforms. Please give him a warm welcome, everyone.
Thank you. Thank you, guys. Good afternoon. Welcome, everyone. Before I begin, just quick show of hands. How many people are here from data fraternity, data engineering, data analyst, data architects domain? Okay, great. 2 people. Thank you. So today I just want to talk something about that most of the data people will relate to it, and the one question that they often come up on a daily basis in front of them, that why analytic systems are so expensive and complex, right? That is the most common questions that they face. So the reason behind is that because modern data platforms are filled up with multiple systems, right? Data lake houses, data warehouses, transactional data, streaming data, and whatnot, right? And on top of that, we are supposed to make analytic system fast, scalable, and affordable as well, right? So before I just go in deep dive, just a bit about myself. My name is Saurabh. I work at IBM as developer relations engineer for watsonx Data. So watsonx Data is a data lakehouse platform for enterprise. So open source is something which I deeply believe in because the one of the topic that I'm covering today, that is Presto, is built by engineers all over the world, globally and collaboratively, right? That is the open source SQL query engine. Let's discuss a problem first, right? A very known problem in the data fraternity, in the data ecosystem, right? That data gravity leads to data fragmentation, right? And the kind of data we have is heavily fragmented. Some of them are sitting in S3, some of them are sitting in warehouses, some of them is directly streaming from Kafka, right? And the problem is that that it never stops, right? It's keep going on, right? And historically, what the industry is doing, that running Spark jobs, massive ETL jobs, right? And that's the truth as of now, yeah. So to do that, there are some consequences as well, right? You are paying for compute hours, you are duplicating the data, duplicating the storage, right? So everything, right? You are paying for everything almost. And the neck behind it that, you have to monitor that Spark job unless it crashed, right? So that is very much required, right? So just ask another question. I'll take how many of you heard of Presto? Okay, great, more hands. So those who don't know, so Presto was developed by Facebook in 2012, and since 2013 is open source, is a MPP engine, massive parallel processing engine. So if you want to run a single SQL query and analyze 10 data sources at one point of time without duplicating and moving the data, that's the beauty of Presto, right? So it is used by most of the enterprises all across globally. And it is a federated query engine, as its name suggests. And the good part is that it supports ANSI SQL. So you don't have to learn anything else to get through with it, right? So if you know SQL, you are good with Presto. What Presto is not, that is very important. So some of think, because as its name suggests, Presto DB, so some of them people think that it's a database, it stores some kind of data. No, it's not. So Presto does not replace the transactional databases, MySQL, Postgres, right? So everything what Presto does in memory, right? And it does not store any data, and it does not, basically, it's not optimized for OLTP workloads. It is optimized for OLAP workloads, basically, right? Just to give a high-level architecture. So Presto follows coordinator worker architecture, basically. So where coordinator is called as the brain of Presto. The job of coordinator is to parse the query, plan the query, analyze the query, and break it down. Where the worker job is to basically do all the muscle lifting, all the heavy lifting, right? Do all the distribution of the task, reach out to the data sources. Basically, all the heavy lifting which the engine is doing are done by worker side. There is a third portion as well. There is a third thing as well, that is connectors. So basically, the connectors are the translator for the data sources. So if you are connecting MongoDB as a data source, or if you are connecting Postgres as a data source, right? So connectors are the thing which basically translates their language to Presto, and then Presto is able to query the data, right? Apart from MySQL. So there are 4 key values where Presto fits in. Basically, where are the 4 key values? I have tried to things keep tightened. So Presto provides these 4 values if you are owning a data lakehouse, or if you are owning a data ecosystem, analytics ecosystem, right? So federation, that is which we discussed a bit ago, that if you are having a data and which is sitting in object storage, or in S3 storage, or Kafka, or streaming data, or anything, right? So, and you want to query the data at one go, right, without moving or duplication, you can do it through federation. The lakehouse support, right? Now the data lakehouses are so smart, so modern, so feasibility have been incorporated in them. So if you are using any table format, file format, right? Apache Iceberg, Apache Hudi, Delta table, right? Avro, right? Or a file format, different kinds of file format. So Presto is very much well optimized for them as well. So the Presto also supports the lakehouse patterns. Third thing is cost acceleration. If you are owning a data warehouses, so you might be facing that one issue, that at the high peak workloads, it involves the cost also. It increases the cost, right? So that's where the Presto comes in the picture, where it separates the compute from storage, basically, right? So you own the storage, and Presto just needs the compute, right? So Presto reads the data and just consume the compute part. You don't have to duplicate the data and just give it to them, the Presto, right? And the last one, that is tuning and mechanics. So if you are worried about the performance and the query optimization, so Presto handle it beautifully inside the cluster. You just have to make some tunings, just make some things work out, and you are good to go, right? So you must be thinking that, yes, obviously federation is there, so obviously performance issues will be there. Yes, obviously, right? But you can fix that. You can do it through tuning. You can make it, right? But the good part is that how it happens inside Presto. So it happens due to the SPI, that is service provider interface, right? So SPI works, SPI is the main component here, which is able to communicate with all the data sources through through the connector, basically. So SPI knows what is the best query, basically what kind of the query optimization I have to follow, what amount of data I have to read, basically. So that's how the federation is possible with Presto, right? So yeah, that's what I'm saying. Presto separates the compute from storage. That's how it works beautifully with it. That's a single query example if you want to take an example that how it works. So as you can see, there is a single SQL query, and which is able to query the Postgres table, and if you want, your Iceberg data lakehouse, right? So suppose if you are querying a small Postgres table, suppose of 10 MB or 50 MB, and you are querying at the same time through federation 100 GB data lakehouse, right? So through that, you can achieve this. So this is SQL queries as an example of doing how to do the federation. So yes, these are some parameters. These are some tuning which Presto can optimize for it. That is CBO, cost-based optimizer, join reordering, dynamic filtering, and pushing where predicate push down, right? So Presto automatically applies predicate push down on the query wherever required, right? So these are some optimization technique which is happening behind the federation. Yes, so as I mentioned, Presto is very much well supported with Apache Iceberg and all the data formats, table formats with for the lake houses. So if you are your maximum data is inside the object storage, right? So you can bring it to the table format, and you can query beautifully with the Presto engine, right? Without duplicating and moving the data within the lakehouse itself, right? So that's why Presto is also called as the query engine for the lakehouses, right? So because object storage does not have any ability to itself to make metadata management and all these things. They do not hold any structure or anything, right? One of the major reason behind that when your data grows, your metadata will also be the most important part of it, right? Especially in the data lake houses. So metadata pruning is what Presto is very good at. Presto do the metadata pruning, that if you are running the data, if you are querying a data, so it analyzes the query and check out that which metadata file has that relevant data, right? And Presto reads that only metadata file, right? Because Apache Iceberg and all the data lake format, file formats, table formats will be owning their own manifest files, the data metadata files for every transaction they do. So it improves the performance of Presto drastically, because it's reading only that data which is required, not reading unnecessary data which is not relevant for the query, right? Or user has asked for, right? That is also very important, that how it works on the cost optimization part. So if you are owning a data lake house, then you can use Presto with Iceberg with most of the read part, if you are reading the data at a very high level, right? And you can use other tools like Spark. So you must be thinking that Presto is separating the compute from storage. So obviously it will is not eliminating the Spark jobs, right? Basically, it's an alternative to do the low latency queries, right? And high performance distributed querying, basically. So you can reserve the maximum part for your the processing jobs, and for the read related part, and for the analytical queries, high performance analytical queries, you can use Presto with Iceberg or with the data for the table format that you are using it. So that's how you can save a lot of cost part of it if you are owning a data warehouse. So that's my favorite diagram. Okay, so as you can see, Presto queries are dancing inside the club, right? But the reason behind is that you can do some tuning on a part of it. So for example, if you have multiple teams which are using Presto cluster at a concurrency level, right? At the same time, they are using Presto cluster. So obviously you need dedicated memory or dedicated execution time for your CPU, right? So you can do that. You can do that tuning on Presto side, which is called as resource groups. So resource groups are designed in such a way that you can allocate dedicated CPU, compute hours, and memory and everything to a dedicated team, right? So for example, your marketing team just needs 10% of your total CPU bandwidth, and your analytical or your data team needs the 80% of your. So you can do that. You can just tune the resource groups, and you can do that. Otherwise, if some user randomly ran a query, so the Presto cluster will be consuming most of that, and the Presto cluster or the cluster will be down, right? So you can manage that through resource groups, right? So yeah, and as Presto is completely written on Java, so the JVM, you can tune the JVM as well, that how much how much memory you want to allocate to that particular Presto cluster. So that will also help in without doing the OOM out of memory kills. Spill to disk is also a very nice feature which is in the Presto, right? So if you are executing a query which is demanding extra memory than the allocated one, right? Allocated to Presto. So you can spill that intermediate data to a local, to a disk, right? So that is how you can success your query without, obviously there will be some sacrifice of latency, but your query will not fail on that on that part, right? Your query will be executed successfully, and you can do that through spill to disk method, right? So these are some tuning techniques. This is the most important one, that is the caching and history-based optimizers. Every data team has their favorite table, right, which they query every day, right? Like sales one or any table which they are querying on a daily basis. So HBO, history-based optimizers, to learn from that, that this person, this team is using that query on a very oftenly, right? So how we can optimize. So it will reduce the latency of giving the results at the runtime. So Presto will work on the HPO part. The HPO will learn the query pattern, and the Presto will query the data with the same table without taking the extra time, the extra latency, basically. So HBO is, and caching supports, Presto supports caching through SSD, that is Alexio caching, right? So you can enable caching and save a lot of latency on that part as well. Yeah, so but most of the time what happens that because a lot of cloud issues or compute issues, sometimes it happens that because cloud outs are inevitable, right? They cannot be avoided. So query can be retried at the time, right? If your query is in the middle and it's about to fail, the coordinator will try not to fail it, right? It will do an extra attempt to make it successful, and it will make an extra attempt in the backend to go for the data sources and query the data until it's completed through fault tolerance method. So it's just a tuning method which you have to enable inside the Presto. So I think these are some blasts. So Uber runs Presto on a very large scale level, right? There's some cluster details which they do it. Yeah. That's how they solved one of the biggest challenge inside Uber, right? So Uber was facing a query throttling, and they did it through Presto Express. They developed a methodology called Presto Express, and which they allocate dedicated space to long batch queries and dedicated space for small queries, right? So that's how they basically separated the compute part. Yes, this is the most important one, the Presto C++. So Presto is completely on Java, but Presto worker is on C++ now. So the Presto team has decided to not completely be on Java. So the coordinator will be on Java, but Presto C++ workers will be on C++. So that will handle the garbage collection and everything, and vectorize execution as well. So that is the future of Presto. That is the project which is known as FOSSASIA as well. So the coordinator will always be in Java, but the workers will be on the C++ part. That is open source team is moving towards it. Right, so this is something, if you can, if you want to join, if you're an open source developer, please contribute to it, right? And be the part of the ecosystem. Thank you.
All right, thank you a lot for the sharing. Unfortunately, we just very on time and we don't have enough time for the Q&A at the moment. But please feel free to reach out into our speaker after the talk. I believe like he will be very happy to answer any questions after that. So yeah, thank you so much.
Thank you.
All right, now we move into the next talk now. We will have our speaker today, Ankin. He is the Director of Services in Anternity, and he's going to share with us about the talk for scaling real-time analytics on iBurst, introducing the project Antalya. And everyone, please give Ankin a warm welcome.
All right. Hello, everyone. Okay, we're coming towards the end of the day 2, I guess, day 1 of the event. So people are getting tired, and let's get started. So we're going to talk about Project Antalya today. And I usually start my talks with a trivia, but with a sailing trivia. But today we're going to have a trivia on this one. So Antalya. Does anyone know where is Antalya? Okay. Okay. You can say. Okay, so he knows it's a big province in south of Turkey that's facing towards Cyprus, and that's basically one of the largest provinces in Turkey. And now the new name is Turkey, and it has various historical sites, Roman, from Roman Empire and others. And okay, another quick question: does anyone know what this is? Have you ever seen it? This gate over here. No, it's not Troy. Troy is in the west. Yeah, that's the opening of the Dardanelles, the Gallipoli. Actually, that's where the Troy is. I don't know if I have a clicker over here that I can show you. But this is Hadrian's Gate, actually the Roman Empire. That Hadrian visited the city in 130 AC. So it also has a 40 kilometers beach. That's public beach that you can go and swim any day. And of course, there is a lot of resource at the end of that. This is only very unique place in Turkey that you can ski and swim at the same day, because there's a ski resort at the top of one of those mountains. You can basically go skiing and come down and swim in the same day if you're crazy enough. And also there's the waterfalls that goes into the Mediterranean, which is very rare, and because it's not a forest area, it's coming down from the mountains. And let's get started. So my name is Alkan again. I work at Altinity. We do ClickHouse support and services at the cloud, also and on-prem at the support level. And I run the support team and the services. And here's a little bit about myself. If you aren't connected in LinkedIn, please, my nickname is AskDBA. Like I said, I'm born to sail, forced to work. I do a lot of sailing, but in between I co-author books and do some community events, speaking about conferences, blog posts, webinars, seminars, so on and so forth. So please get connected with me if you have any questions later on, because we may run out of time. So another question to the group over here: has anyone heard about ClickHouse or work with ClickHouse? Okay, few people. We have some. Okay, ClickHouse was born at Yandex. It is designed for real-time analytics. We call it real-time. It's near real-time, and it's a C++ that's written in pre-AI era. It's written by by people, and it runs anywhere. There's distributions for almost on laptop and anywhere you can run it. It's a columnar store. That's the one difference between the other databases, and it's got like amazing features like parallel execution, and of course it's open source with the Apache 2.0 license. The use cases are here in generally for large scale. It is designed for analytics, but also used for observability, like if you have a large system. And nowadays we are seeing implementation of LLM monitoring, and also like financial analytics is when we say financial, large financial institutions are using ClickHouse for analytics. Also crypto companies are actually utilizing. It's a stable sub-second response time and very fast. So this is the architecture. What's under the hood is a ClickHouse server. There's a vectorized parallel query execution engine, and it runs on a merge tree. Merge tree is an engine that it runs. It consists of parts, and its data is written into parts and then merged into a data block that the database can access, and also has a S3 compatible object store that you can actually interact with merge tree data in the S3, and the coordination within the cluster is done by the keeper. We have a ClickHouse keeper. Originally it was a zookeeper. Apache Zookeeper was the coordinator for if you have a replicated environment. The traditional event pipeline is basically you have a data source that could be any other open source database, MySQL, Postgres, or any other data source, and that gets written into Kafka, and then usually this is how it's being utilized in large scale in production, and then goes into ClickHouse, where the merge tree is receiving the data and then combining the parts into building real-time dashboards and access to the systems that you are actually monitoring into. There's also another piece that is not mentioned over here. There's a sync connector that's part of the Alternity open source tools that can also receive with a Debezium driver from other sources like MongoDB or other object stores, any data that maybe it's a CSV file you can actually import into. So where is the problem are we trying to solve with Project Antalya? The block storage is expensive. Now, it used to be CPU was expensive. Originally, if you remember when the cloud was coming in, the CPU was very costly. Then CPU with high memory was like special nodes, and it was more expensive. Today, both of them are cheaper compared to storage because the block storage, the data is grown, and we have more data, and the demand for fast storage is high, and the block storage is expensive, and we need more scalable storage solutions. And when we talk about analytics over here, in the use cases over here, we are actually talking about petabytes of data. So it's no longer terabytes, we're talking about petabytes. We have customers actually utilizing approximately 20 petabytes of processing, 20 petabytes of data that they had to reduce their TTL to 3 weeks, used to be 6 weeks because there's not enough. These are like LLM providers, they actually keep logs and it's not impossible to keep them in the block storage anymore. So so when we talk about ClickHouse, it works really great on the columnar store, and we get millisecond, sub-second response time on a very large data set, like 196 million rows. That's a very popular open source on-time data set that we do a lot of tests. It's a US-based airline traffic control system is stored and it's shared. You can actually run analytics on it. These are the tests showing over here. So when the data is that large, you're looking for if this was the universe and then the planets, and then this would be Jupiter over there. And basically, if you selected everything, it would be like this large. But what we do is we only read the columns that we need. As in this example over here, we only read like 3 columns, carrier, year, and the canceled flights. And then we reduce that, and ClickHouse does this automatically. And then we actually compress that, and then we only compress and read with the multiple threads. Then you actually get only very fraction of the data that you need as a result from this query. And that's why it is actually it takes less than a second to process. So, okay. And let's continue on this one. So we have also a new era and a new workloads. What is that? It's AI. So we got like AI workloads coming in on top of the system that runs AI and logs, maybe observability, the hotel implementations that spans across hundreds of nodes and clusters. And then we also have MCP servers connected to the databases now. Alternity also has an MCP server designed for ClickHouse. So if you are actually trying ClickHouse and some sort of an AI implementation, you can use this nice lightweight Go application that runs on any server without the dependencies to access the database to the AI. By the way, I also do some work around other MCP servers for like MySQL. We do not recommend connecting production data into the AI directly without making a lot of limitations or restrictions. So you do this on the test servers. So when we actually have this data is rapidly growing, we have the CPU, provisioned CPU, and the storage. And also, I think someone mentioned earlier today is the IOPS costs, Sergey was mentioning, are importantly increasing the bill from the cloud providers. So you actually want to utilize storage for the object storage. So what we're trying to solve over here is to utilize iceberg tables in attached to ClickHouse. So this way, what we get is we still have all benefits of the ClickHouse, but we almost have nearly unlimited storage and access option to object store. So this is how we're going to try to achieve this project. Project Antalya was born in Antalya for about 2 years ago. Last 1.5 years was development. Now it's a production ready grade. It's been tested in large implementations. So does anyone know? I think we had some Iceberg related talks. Does anyone know Iceberg? What Iceberg is? Okay, a few people. Iceberg is a catalog service. Basically, it runs on the object storage, so it knows where the state of the metadata, where it's actually able to sit on top of the storage to have ability to access like a database table, and that also gives us a some way of interacting with the regular databases like ClickHouse. And in the previous talk there was Presto, and that's also doing something similar with other data sets. And so Project Antalya is actually addendum to what the ClickHouse works, because ClickHouse is an open source, and we can actually basically add new features on top of it and then release it with new features. So already ClickHouse is already making some improvements onto Iceberg tables, Parquet readers, like you can actually point to an object store and read, ingest that data, maybe run a summary table, and then execute analytics on it. But Iceberg we have actually designed Antalya to go beyond that, and then we can actually separate compute and scale that. So the advantage will be not only accessing and reading, but also scaling this operation overall with that. So upstream is continuing to build. Alternity is building the Antalya on top of it, and then we basically have the builds that also can run both of them, or you can run it separately. We also actually provide like the containers around it. So there is another concept called swarms. So what happens is with the Iceberg data and the Parquet files, when you're actually reading a large data set, this again, you're at petabyte scale, some jobs will be taking longer time because those storage may be very large. And what you need, if you actually integrate the swarm clusters into this ecosystem, we have seen benefits of reading. Basically, this allows us to send a job to background readers and then utilize those without. I got 2 minutes left, so I'm going to run through this a little faster than normal. So the merge tree benefits are loads almost instantly, and there's compaction and built-in and fast. There's very low latency. On the Iceberg side, it's cheaper and fast, and horizontal scaling is out there. There's unlimited I/O bandwidth, literally, and you don't get charged as much as the other storage. And you can share with other applications, like you can actually point your ClickHouse, and you can point other applications that you want to ingest from the. So basically, source is that. We're going to skip this one. There's like some performance comparison between the merge tree and the Iceberg tables. Basically, both of them have different states when they're hot and cold because of the cache layers that you're reading. So the results, that's why the results are changing. But overall, we're seeing a benefits of using this when the swarm clusters actually help with unlimited CPU and RAM wins. This helps the cluster to be utilized faster. So we're going to skip this part. There is also a concept called hybrid engine that combines these two, whether it's merge tree and the S3. What we can do is basically without manually making any modifications, we can move data between the hot tier to the cold tier. So ClickHouse has already have a tiered storage level. You can do hot, warm, cold, and then you can define your storage layers, but that will all happen within the merge tree family. If you need to do that in the Iceberg and object store, basically S3 compatible storage, you need this type of hybrid engine, which is also kind of another invention of Project Antalya. And then it's basically an engine that is added to the database engine. And if we actually put all the pieces together, this is the outcome. You actually have the Kafka stream coming in, and then you have the merge tree with the ClickHouse access, and the hybrid table combines the Iceberg and the object store all together. as in this picture. Okay, so I think I am almost about time. And you can also do tiering between the hot and cold storage. So from what is come out from this is they both have strengths. We wanted to combine them. And again, we listen our customers. This is why this came out. And the cost is the primary concern of the analytics and the storage systems that's running in the cloud. And the viable option to overcome that was coming up and utilizing object stores. So this helps to that. There is some AI, of course, I need to mention this, there's some AI movement happening. This, with the AI workloads, the storage needs and the cost will also become crucial to the ecosystem that we actually want to solve. So there's more information about all these demos and the repo. We can also come in and ask questions on the Slack, and you can give it a try. We also have, just to wrap up this talk, we also have an event tomorrow, on Wednesday, not tomorrow, the day after tomorrow at Perkona University. We're going to talk about databases. I will talk about MySQL, MCP server, and the vector search and AI workloads over there, along with some other database people. If you're actually interested in, please sign up and join to that event also. Thank you very much.
Thank you so much, Ankin. Do we have any questions for our speaker? All right.
No
yeah.
questions.
Thank you so much.
All right. Thank you very much.
Yeah. Please feel free to reach out to Ankin after the session today if you have like any questions in the upcoming days. So we're going to move into our next talk now. All right, everyone. We're going to move to our next talk now. We have one of the very wonderful speakers here. We have Jordan. He's the founder of Tailstrap.com, and he's going to bring a session today about building data dashboard owned in SQL. Everyone, please give him a warm welcome.
Hi, everyone, and thanks for coming to the talk. So I'm going to talk about data dashboards and visualizing data. And if I'm thinking of data dashboards, some software like this comes to my mind. I don't know about you, but I'm a software developer, and I don't really enjoy UIs like this. So I actually don't even like to use my mouse. So I prefer to use the keyboard to work. And eventually I got so annoyed and frustrated to work with interfaces like this, not specifically this software, but AI UIs with this many buttons and so on, that I decided I want to do something about it. So I was thinking to myself, well, I don't want to work like this. This feels slow and it feels easy to mess something up. What would be the ideal tool for me to visualize data? And I'm just thinking, well, I actually don't want to bother visualizing data at all. I just want to worry about which data am I interested in, and then I want to hand the data to the computer and let the computer do the visualizing for me. And when we're talking about getting the data we're interested in, for me, I actually like to use SQL to get data I care about. I think it's a great tool to describe which data I want to have. And so I was thinking, okay, let's explore that approach. And let's look at some SQL. How can we go from SQL to then visualizing it as some graph or something like that? And if we look at this example here, we can see we already have a separate query just to fetch the title, and then we have the actual data we want to show as a graph. And this SQL essentially describes all the data that we need to then render a graph like this. So how can a computer go from this SQL to show us a graph? Well, in theory, the computer can look at the shape of the data and know, well, this looks like something I would graph as a chart, right? But then there's not just one way to visualize exactly this data. So this chart here with the bars is great to compare the bars with each other. Here, each bar is a week, so you can compare over time. How does my data change? How do the bars change, right? But if I don't want to compare the weeks over time, but I want to compare categories with each other instead, then another chart might be better. So in that case, maybe a line chart shows me right away, like, how do the different categories compare to each other? And so somehow we have to make a decision here how we want to visualize the data, but depending on which questions we're asking. That's something the computer cannot decide for us. So how do we do that? Well, can we somehow tell the computer what kind of visualization we want and just give the computer that as information as part of the SQL somehow? And if you look at this, this might look a bit weird, but this is all just valid SQL. If you haven't seen this double colon notation here, that's basically a way to do type conversion in SQL. So when we look at the first line here, the text here, we convert it to the type label. But label here, it's not a standard SQL type, right? So we convert that type here, and underneath it's still just a text, but we defined a custom type, and that's something many SQL engines allow you to do. And the type label then underneath is a text, but it's a custom type that just describes in the type information how we would like to visualize that. And then we do that for all the other columns. And by adding this extra information, this SQL now describes how we want to visualize the data. And by just looking at the code, the computer can then do that for us, and we can encode the decision we made about how we want to visualize it. And then if we want to change it, we can just change bar chart to line chart, and then the graph would change, right? So this works. We can describe a single chart like that. But if we think back to the beginning, we were not talking about only one chart. We were actually looking at a whole dashboard. So how would we do that? Let's look at an example here. On this dashboard, you see we have a bunch of different visualizations. And basically, we could just take this and break it down. Okay, we have 5 cards here. So we can describe each of these cards with SQL the same way we did before. And that works easy enough. But then at the top, you probably saw there are some filters as well. So what happens if you want some interactive elements in a dashboard? How would you do that in SQL? Well, let's look at this drop-down to select a category. We could describe that drop-down to a computer, right? So the computer can know how that I should render drop-down somehow. Well, we have to somehow say what this drop-down should be called, and then we have to also specify which data a user can select from. And we can do that in SQL, right? We can return a list of options, and then all we have to do is somehow say this is a drop-down, and then the computer can render it as a drop-down. Now, once a user would select an option here, we somehow want to update the rest of the dashboard. So if we look just at this count here, we just calculate a count over a bunch of rows of data, and we could then filter that accordingly. So by adding a where clause, we add a filter here, And instead of hard coding some filter, we can treat the drop-down as a variable. Here we have a helper function in SQL that just refers to that drop-down category, and the same for the date picker next to it. And that way we can use SQL to dynamically define dashboards that include some interactivity. So this is basically all the elements we need to describe a dashboard like this with only SQL code. So once we have that, our workflow can look something like this, where you can open your editor of choice and then just start writing SQL. It's just code. This is actually what you see on the screen is the complete code to define this specific dashboard. And then we just need the tool on the other side that takes that SQL, runs it somehow, and shows a dashboard to us. The great thing about working like this is that now we just use our editor. It's just code. That means we can basically build dashboards the same way we build any other software. So that means we can put it in Git. We can, of course, use our editor. And we don't even have to write the code ourselves, right? It's code, so we can ask an AI agent to write it for us. And I want to work that way. It feels much simpler for me than going back to a UI to build dashboards. And now we only need that other tool that runs that code for us. And if we think about running SQL, usually that works by taking the SQL and sending it to some database, and then we get back some data, right? How would we do that here? And so this is where DuckDB comes in. So if you haven't heard of DuckDB before, you can think of it similar to SQLite. It's an in-memory database, in-process database. So it runs as a library in your applications. You don't have a separate database server that you have to connect to. Instead, you just have a library in your application that allows you to run SQL code. And interesting for us is that DuckDB cannot just query its own data, but it can query all sorts of data sources. So you can treat it as a SQL engine to then query different data sources. So you can, for example, connect from DuckDB to your Postgres database, or you can also query things that are not databases. So you can directly query CSV or JSON files, either locally or files that you have on a cloud storage like S3. And if there's any data source that you want to query and DuckDB doesn't support, DuckDB has like a flexible extension system. So anybody can create extensions for new data sources. For example, one I like to use is for Google Sheets, so you can directly connect to Sheets and query them. And that's great. With this, we can then just write SQL and query any data we like. We can put these things together, and then our code can look something like this, where we have a single select statement. We select from a bunch of different data sources. So here, S3, Postgres, a Google Sheet, we join them together, and we turn the whole thing into a chart right away. So these are basically all the pieces we need to build a dashboard. And what I talked about is not just theory. I implemented this idea. It's on GitHub. It's called Shaper. It's open source, so anybody can go and try it out. And it's actually a single Docker container you can run anywhere you like. So I prefer running this exactly where my data already is. And that way, I don't have to send my data just to analyze it to some cloud provider or something. So it's open source. You can run it in your infrastructure. And if you want to find out more, you can check out the docs. And with this talk, I just want to not talk specifically about my implementation. Of course, check it out. I'm happy to talk about it. But more in general, encourage you to think of visualizing data as code. And I think SQL is an interesting approach to do that I haven't seen explored that much before, that you directly combine your analytics code with these additions to then visualize the data. And with that, if you have any questions now or later, feel free to ask me, and thank you.
for the sharing, Joring. Do we have any question for Joring right now? Yeah. Otherwise, please feel free to reach out to him after the talk if you have anything you want to chat, especially for this dashboard. Yeah. So now we will welcome the next speaker now. Yeah. All right. Hi, everyone. We're gonna to start the next talk now. One of the very exciting talk for me. So please welcome our next speaker, Alexander. He's gonna to talk about scaling vector search in distributed database, the YDB journeys. Everyone, let's give him a warm welcome.
Hello, my name is Alexander Zivaykin, and I'm working with an exciting project named YDB. I have the privilege to share with you my passion, AI and big databases. And one of the interesting tasks is how to implement vector search in a distributed database. YDB is a distributed database that combines high availability and scalability with strong consistency and ACID transactions, dealing with millions of transactions per second and tens of petabytes of data. And one interesting options about YDB, having built-in vector search engine simplifies many things. We do not need a complex infrastructure. Scaling and making production easier, for example, are Herculean tasks. For example, sharding and replication on thousands of servers requires enormous expertise. And we in YDB have already solved these complex tasks, and implementing yet another feature like vector search is just a piece of cake. Let me quickly recap what vector search is. An embedding is a way to convert a piece of content, for example, text, video, audio, into fixed size numeric vector. And key idea is similar meaning means vectors are close. So instead of key vector search, we simply produce nearest neighbor search in a vector space. And here comes vector database. It simply stores and search vectors. On the left, you can see indexing process. Many images, for example, pass through encoder, and vectors are produced and stored in the vector database. And on the right, we can see a user comes with a query. Query is also passes through the encoder, and we can simply find nearest neighbors within vector database. That is it. But different scenarios appears. There isn't one single approach for vector search. They could be exact search of user facts. Exact search, usually user have tiny amount of user facts. And they could be approximate search of all facts. And these cases require different indexing algorithms. Let me start from naive approach. This is the most straightforward sequel. At first, we simply find by user IDs and then order by cosine distance. It is attractive because it's simple, it's fully transactional, and also updates are immediately visible, of course. But the problem is obvious. Without an index, it becomes a full scan. Here, our measurements on a big data set. The scaling trend is a huge point. For example, by 1 billion rows, the typical query takes approximately 2 seconds. So the naive approach has many advantages: no extra indexes, ACID correctness, immediate updates, but the drawback is obvious. Full scan doesn't scale. And first, we introduced an approximation approach to reduce the scan cost. There are 2 steps. At first, we can, table has 2 columns, bit embedding and float embeddings. Bit embeddings require 32 times less space. And that is why we can search by 2 steps. A coarse search using bit embeddings, and a refinement step which uses smaller candidate set, but it's search using float embeddings. This is already useful, but it is not still a final solution. For a huge data set, we need an index with predictable latency. Let me start from quite strict requirements to this index. Many of those are originated from the very nature of a distributed database. Our goal is to store billions of vectors. It means that index should scale in a linear way. Another quite a strict requirement is to be both synchronous and consistent. Many algorithms have already been invented, but they do not suit our very strict requirement. YDB is a distributed system. It means that automatic scaling is important. On the other hand, YDB has strong consistency. It means that index should be also consistent. Let me switch to the internals of our vector index. on the left, we can see vector space split into several vector clusters. Every cluster has its centroid, and all the centroids form a classical information retrieval index with posting lists. We can see it on the right. Here are centroids in the buckets, and every centroid has its own posting list. And the search step is quite trivial. For example, if a user query passes, we at first find appropriate cluster and then finds within that cluster. That is it. But this approach has also one drawback. If a number of vectors is huge, the number of clusters is huge also. So we should look at some hierarchical approaches. The solution is to use some space pruning algorithms. Maybe some of you are familiar with so-called R tree. There are small red clusters. They form bigger green clusters. So first, big black clusters are formed. And this very structure can easily cope with a huge amount of clusters. And now let me return to our vector index. We managed to store, we use the same hierarchical structures like folders on your file system. For example, green clusters form blue clusters, which becoming bigger and bigger, and so we form a tree. And we managed to store this tree structure in several usual data tables. And do not forget, we have a long-term experience in YDB of how to scale such tables. For example, a usual hour table can even store thousands of vectors, millions of vectors, billions of vectors. Our tables are elastic. And that is why we automatically get elastic vector index, which is capable of storing billions of vectors. Another feature is a filterable vector index. The original query contains where predicate, and internally it's enormously difficult to process because you can't filter before vector index. Vector index optimizes only whole queries, and you simply have to full scan if you filter before vector index. You can't filter after vector index because vector index produced some smaller candidate set, and the number of candidates may be not enough, and you have to repeat query increasing top key limit. It affects latency. So the solution is to implement filtration capabilities inside vector index. We have created well-known secondary index on the top. In our example, it is index for user IDs, and every user ID has its own vector index. The idea is brilliant by its simplicity, but some believes that it's too wasteful to have too many vector indexes. For example, if a number of users is million, we have to have a million of vector indexes. Of course, it becomes complex. But for our implementation, that doesn't matter. Recently, I have told that we have usual data tables to store our index. And so we simply turned from millions of vector indexes to millions rows in tables. And it's quite simple. Here is the final picture. The red filter table is for storing user IDs. And we reuse the same table hierarchy. At query time, the filter predicate selects correct subindex, and we simply traverse through the tables to the correct answer and runs within appropriate subindex. So we get correct top keys without retries and without full scans. Finally, I want to show you how to cope with index update. A new vector is added. It's located in some cluster. And we simply put the vector to the end of posting list of that centroid. A transaction is used. That's very important. So the update is consistent, strictly consistent quite brilliant. Let me conclude by summarizing the main parts. YDB is a distributed system that combines high availability and scalability with strong consistency and tacit transactions. Recently, we are moving towards AI. Thank you for your attention. Feel free to ask questions.
A lot for sharing with us today, Alexander. If anyone have any questions at the moment, yes, I can.
Vector question. What library is YDB using for the vector indexes?
Internally, YDB is written in C++, but we have a lot of SDK written in many languages like Python,
No,
Java.
no, no. The index library for the vector index. Like you index the vector data, right, into HNSW or?
HNSW is a typical index, but we intentionally do not use HNSW because simply do not passes our strict requirements. HNSW do not passes them. For example, it do not scale in a linear way.
Okay, so it's basically using YDB has its own index library for vectors?
Exactly. We have created index like this with a hierarchy of clusters. We can scale in a logarithmic way. We can store billions of vectors, and our index is really elastic. For example, I may start from 1,000 of vectors and add more and more vectors, and quite quickly I can go to 1 billion vectors, and index simply scale. Just believe me.
Thank you.
It scales.
We have to talk. Thank you very much.
Thank you so much for the sharing. Yeah.
you.
If anyone have any questions, like feel free to follow up with our speaker after the presentation today. Yeah, we're gonna to move into the next talk now. All right, everyone. Are you guys ready for the next presentation today? So we have our wonderful speaker, Alexei, today. He's the principal software engineer of a Lab. He's going to share with us about the PolarDB, scaling your PostgreSQL workloads. Alexei, I really appreciate that you spent time with us today and stay until this session. We cannot wait for your talk. It's your stay now.
1, 2, 3. Oh, okay. So, hello everyone. Good evening. Everyone is probably tired by now after the full conference day. Don't worry, this talk is going to be light on technical details. It's just a high-level overview of a complex but otherwise fascinating technology. So I'm going to be talking about PolarDB, explain what it is, and how you can use it to scale your Postgres workloads. A few words about myself. I'm a long-time open source user and contributor. I installed my first Linux about 30 years ago, which is hard to believe even for myself. I made my first open source contribution about 25 years ago. And for the last about 20 years, I've been involved in database development, mostly the MySQL ecosystem. Made some cool contributions to MySQL, Percona Server, Percona Extra Backup. And some of you may know me as the author of Sysbench, which is a popular database benchmark utility. But today I'm speaking in a bit different capacity. I'm going to be talking about PolarDB, which is the technology that I have been working with recently. And here's a brief clarification. There are multiple PolarDB flavors. It's basically like Amazon Aurora. There are multiple products and projects that have PolarDB in their names. Some of them are based on MySQL, some of them are based on Postgres, some of them are only available in Alibaba Cloud. This talk focuses on the open source project named PolarDB for Postgres, and I will be referring to it as just PolarDB throughout the presentation for brevity. Okay. So, what is it? It is a fork of Postgres created by Alibaba and released to open source a few years ago. It features the cloud-native architecture with disaggregated computing storage, which makes it elastic. That is, it is cheaper to scale compared to traditional Postgres or traditional databases. It also has HTAP capabilities. Basically, it can do analytical processing through EPQ and PX technologies. And it is fully 100% Postgres compatible. It works with existing Postgres applications, drivers, and tools. It also supports standard PostgreSQL syntax and again extensions, which is a pretty major feature, right, in today's world. Postgres has a huge ecosystem of applications and extensions and so on. So being fully back-to-back, version-to-version compatible with Postgres is actually a major feature. And Alibaba originally released two branches of PolarDB. The one was based on Postgres 11, which is currently end of life, and another one was based on Postgres 15, which I think is still supported until next year. At Awide Labs, we see three realities. The first one is that the technology itself is awesome. It is a robust, mature database engine capable of supporting a wide range of workloads. But at the same time, we feel that our impression is that it has very low visibility. Yes, Alibaba has invested a lot of resources into promoting that open source project when they released it, but they were mostly doing it for the Chinese audience. So our impression is that it's under-promoted and mostly unknown outside of the Chinese technical circles. And it also has an uncertain future. The open source project has received almost no updates after the initial release. They are basically rebasing the version 15 branch on minor Postgres releases, but that's about it, right? So despite these challenges, we believe in the core technology, and we have already enhanced it with our own optimizations and features. And our commitment is that we are going to open source all our improvements, ensuring that the project has a future that is available to all users, regardless of whether they want to run it on their own hardware or in the cloud. So what makes PolarDB different? Before we dive into that, I would like to establish a baseline. This is a typical architecture for a traditional single node database, right? It has certain layers like SQL processing layer, parser, optimizer, executor, there's the transaction processing layer, there's some index data management, buffer pool, WAL or transactional log, and there's storage or disk directly attached to all those layers. And all of these layers in a traditional database are running within a single server, right? This architecture has served us well for decades. It is simple, it is well understood, it provides good performance for many applications, but it has certain challenges when it comes to scaling, right? When you outgrow capabilities of a single server and you need to scale, your choices are either replication to scale reads or sharding to scale writes. And they both can be either expensive or inefficient or both. So with this baseline, let's look at how distributed databases handle it differently, the scalability problem. So this is where things get interesting. When designing a distributed database, the key question to ask is where do you split compute and storage? Different databases answer this question differently. And depending on the answer, I mean, the answer, the split point, determines key characteristics of a distributed database. For example, we have Greenplum and Citus, which are sharded databases, and their disaggregation point is above all layers, which basically means there's no disaggregation whatsoever. Right? Every cluster node is a fully self-contained server with its own SQL processing layer, transaction processing layer, and so on. Then we have databases like Spanner, YugabyteDB, CockroachDB, TiDB. They disaggregate below the SQL processing layer, but above the transaction processing layer, which means that on compute nodes, they do SQL processing, and then they distribute transactions into the storage layer. Then we have databases like Aurora, Neon, AlloyDB that implement the log is the database concept, first introduced by Amazon, and they disaggregate between the index and data management layers and buffer pool and WAL management, or somewhere in between. There are some subtle details there. And PolarDB disaggregates at the lowest possible layer between disk and everything else, and that makes it unique. I'm not aware of any other databases that do the same. And that has certain advantages. First of all, the amount of code changes required to transform a traditional single node database into a distributed database. With this approach, the amount of code changes is minimal. And that usually directly translates into higher compatibility. If you are able to keep up with the upstream server development, right, with less code changes, that means you have higher compatibility, version to version, back to back. Now, let's look at what makes PolarDB similar. If you look closer at the same diagram, you'll notice that there's one fundamental property that defines, that can categorize all those distributed databases into two categories. If the disaggregation point is above transaction layers, then the distributed database can have multiple nodes accepting writes. If the split point is below the transaction level, then the database can only have one node accepting write, which is one primary node. And in this sense, PolarDB is similar to Aurora, Neon, and AlloyDB. It can only have a single primary server, and what was the trade-off here? So with multiple writer nodes, of course, we can scale writes by adding more nodes to the cluster, which is good. But the database world is full of trade-offs, and there's always a but. In this case, the downside is that higher complexity, higher latencies, and some compatibility trade-offs. It's simply impossible to, for example, implement a fully Postgres-compatible database with that architecture, like Spanner, Yugabyte DB, and CockroachDB, because to be fully compatible with Postgres, you have to be Postgres. And Postgres has simply not been designed with the multiple writers concept in mind. So the key innovation of PolarDB is the shared storage architecture. And it works like this. The primary node writes val and data to a shared block device over the network. And this shared block device can be anything. It can be EBS, Ceph, NBD, or SUN, anything that can be represented as a block device and accessed by multiple nodes can be used for PolarDB. And then you can scale reads by adding multiple read-only replicas from the same. They read data from the same storage. They can be scaled independently from storage, and adding read-only replicas is cheap and quick. They're basically stateless. They use the shared storage to read the data. So first of all, they don't need the same expensive hardware, right? They can only have a very cheap disk to boot the operating system and the database server itself, but they don't need the powerful disk subsystem, right? And then when you add them, they are basically ready to serve queries immediately. You don't need to transmit, I don't know, terabytes, petabytes of data to make them ready. And accessing data on the same storage requires coordination because Postgres basically requires a file system underneath. It relies on file system and files to organize and manage data. So we need a file system, but it needs to be distributed to work on shared storage, and that's why PolarFS has also been created by Alibaba. They released it to open source as a separate project. This is a minimalistic distributed file system, right? It was purpose-built for PolarDB. It has the POSIX-like API. It features direct I/O, which is also an interesting property because, as you probably know, Postgres does not currently support direct I/O. It relies on page cache, but PolarDB does support direct I/O through the file system. And it also maintains metadata journals, so compute nodes have a consistent view of data. Scaling storage. So there are multiple ways to build storage. Like I said, PolarDB does not enforce or even recommend any specific way to build storage, right? There's a wide variety of different architectures, all providing high performance, data redundancy, high availability. And at Avaya Labs, we've been experimenting with multiple approaches. And our choice so far is Linux MD cluster over the NVMe protocol over RDMA fabric. This is how it looks. It may look complex, but essentially this is, this storage has been built with commodity hardware and only open source technologies. And this is what we recommend. This is actually works pretty well for a wide range of workloads. Then working from multiple database nodes with shared storage creates some challenges. First of all, there's the cache invalidation problem. Replicas need to know when pages in their buffer pools are modified on primary. Then we need to update. We need a mechanism to update pages. Replicas need to know where to find val records to update outdated pages. Then there's a future pages problem that is specific to this architecture. Primary may flush a page too soon and break val replay on replicas. And some DDLs, well, DDLs are always a problem in many cluster environments. So this is, PolarDB is not an exception. Some DDLs require special handling on the primary. But all of these challenges have been resolved by Alibaba, and we have performed extensive testing to verify that. Now, PolarDB basically redefines what replication means. Since we have the shared storage, and all data is written to that, while it's written to that, then basically only metadata is replicated from primary to replicas. This replication can also be either synchronous or asynchronous. And that has some direct implications on transactional consistency. So with synchronous, this is usual trade-off. With synchronous application, it guarantees most recent data can be reconstructed. The cluster behaves as a single node database from the consistency perspective, but it's bad for write latency. And a synchronous application, replicas may lag behind, and PolarDB offers so the open source version of PolarDB offers only a single level of consistency, which is eventual, right? So which is unacceptable by many applications. We have implemented session and global consistency using a custom fork of ProxySQL. Now, PolarDB also offers some HTAP capabilities, and their approach to HTAP is massively parallel processing over the same row-oriented data, which is, as usual, has its own pros and cons. The big advantage is that you don't need ETL to, you can do analytics on fresh data, but the disadvantage is that it only works for lightweight analytics only. It's not going to replace your enterprise data warehouse or specialized analytical databases like ClickHouse or DuckDB. And the planner and executor are based on Greenplum. Oops, what happened? Okay, so high availability and disaster recovery. For high availability, PolarDB is similar to Postgres. It provides the architecture, but no built-in high availability solution. We have basically patched Patroni. Patroni is the go-to solution to implement HI for Postgres. We have patched Patroni to support the PolarDB architecture. And the patch required to achieve that was like a few hundred lines of code, which is not much at all. And for disaster recovery purposes, so the usual problem, when you want to implement disaster recovery, you want to replicate to another data center onto another availability zone. And there's the usual trade-off here with synchronous and asynchronous application. So Alibaba has implemented something interesting. They implemented a special cluster node called DataMax, which basically accepts while but does not apply them, and then it can actually send those files, transmit those files to another data center. If you're from the MySQL ecosystem, this may look very familiar. This is basically the beanlog concept server that is used extensively in the MySQL ecosystem, and I think this is the first implementation of the same concept for the Postgres ecosystem. And finally, PolarDB implements a number of features on top of the basic architecture. Some of them solve some long-standing Postgres performance issues. Others add some new capabilities like HTAP. But the problem is that this feature set is fragmented. Some of the features are only available in version 11. Some of them are only available in version 15. And we have bridged that gap by porting the missing features from version 11 to version 15. And we are already in progress of rebasing PolarDB feature set to Postgres 17. Just to summarize, PolarDB is a cloud-native Postgres. It has the short storage architecture. It has capabilities that provide performance and scale, and it's best for Postgres users demanding enterprise-grade scale with high availability and some lightweight analytics. And at Avaya Labs, we are breathing new life into this PolarDB, and we are going to release all our improvements under an open source license. And that's everything I had to say. Thank you.
Do we have any question for our speaker? One questions. Yes.
Yes, thanks for your talk. I have a question about PolarFS. Is it open sourced? Can everybody use it?
It is open source, yes, but when we started benchmarking it, we figured out it's actually, it doesn't scale well for devices capable of doing millions of IOPS. So we have also heavily optimized it for that scale.
All right. Thank you a lot for sharing with us today, Alexei. If anyone have question for him, feel free to reach out to our speaker after the talk. I believe he's gonna very happy to answer the question of everyone. We're gonna to move into the last session of the database track today. I hopefully everyone excited for the closing of our database track. Let's give our speaker 1 minute for the preparation. In the meantime, I'm going to introduce him to everyone. So we have our speaker here. We have Peter. He is the entrepreneur and co-founder of Percona. He's going to share with us about the AI DBAs, the state of self-driving databases today. Yeah, everything looks very perfect now.
Okay.
Yes. Please give him a warm welcome, everyone.
Hello. 1, 2, 3. No, you've got your filter. Okay. White is yellow, yellow is white. Who gives a shit? I think you guys can read the text and that's what matters. Okay, we are going to talk about self-driving databases. Now, if you look at the term of self-driving database, kind of to get started, that was all invented by Oracle as mainly marketing term. They have been talking about the Oracle Autonomous Database back in 2017. And this kind of idea of self-driving really comes comparing that to self-driving cars, right? Now, if you look at the self-driving cars, we have a bunch of levels, right, ranging from level 0 to level 5, right? And I think it is very interesting to think about the database self-driving in the same way. Now, where do you guys think that the databases are right now? Any thoughts? Yeah. Well, I would say it's level 2 and to level 3, right? That's kind of similar, right, to that. Right. Again, it of course depends, but in reality, a few systems in production, they will self-scale, self-tune, kind of automatically add indexes and so on and so forth. Most databases would use evolved monkeys for that, also known as people, right? Now, I also was looking at this, asked folks on LinkedIn, what is a trust level? Right, and of course, my audience is a lot of DBIs who think that they're very smart and know what they are doing. So you can see the trust level was actually surprisingly low for me. Right, majority of people say no. Modern AI as it is, I would not be able to do that. Now, what is interesting in this case is if you think about cars, right, to compare the analogy, we would see what a lot of people also would not be quite comfortable, while at the same time, if you look at some of the leading self-driving companies, they do now less crashes than human drivers do, right? And a lot of that actually comes because it is not a question of how human is able to operate at this sort of, really peak, but to the fact that unlike machines, right, which are all can be programmed the same way, humans unfortunately have a significant variance of skills and also a lot of kind of variance in attention, right, or level of energy. For example, if I don't make any sense right now, this is because I have a jet lag, right? And at some other times, I can probably, do this presentation much better. I think another interesting question when it comes to self-driving databases is what we are not really looking at the ability of best DBA out there, right? When we are operating our database, we are really thinking about what kind of resources for that you have available, right? What resources you have available, and what is their relationship of opportunity cost, right? Because maybe if you have there your best engineers, you don't want them kind of to be focused on that database tuning, but maybe you want them to be focused on making your product better. Now, let's talk quickly about the database problems, right? What do we really think or what exists in a database space which needs to be driven, if you like? Some of that is spending more than you should, right? A lot of cost questions. If we are looking to optimize the database, we often can reduce our cost. Then we are also looking at performance impact, right? And if database is slow, it impacts our users because they may not be as active in our system, right? Go to stop scrolling TikTok if it becomes too slow, right? And go to Facebook, right? Or wherever. And then also their poor performance becomes for people indistinguishable from downtime. And I would put that in the one bulk of problems, right? Because in many cases it can be, sort of fixed, evolved gradually, but there is also other kind of problems, which is data loss and exposure, right? Which can be, fatal for the business, or at least it can be very, very severe. And I think that is a very big reason why we often want, human who kind of have this legal responsibility, unlike AI involved in this case. What I think is also interesting is what is reality of how much AI can help us to tune the database. And I think that's also interesting from perception standpoint, right? I was asking people in terms of how much performance do you think modern AI tuning tools can get by the database tuning, right? And you see mostly people say, 10, 30 database, right? And that's, quite reasonable what I would expect. But at the same time, if you look at what some of the advanced systems have those days, it can be really several times for workloads which have been very purely optimized. Again, I think that corresponds to my audience, which is a lot of advanced folks which are quite confident in the way. Now, if you look at their database and performance optimization, we can see that can happen in quite a lot of areas. And some of those things, such as configuration changes or scale of environment, right, after scaling, are solved pretty well by modern systems. Others, kind of going on to application architecture, is what's mainly involved is human. Saying, hey, completely rewrite my application so it scales better, redesign the schema and everything. That is not quite there yet. I think what is also very important where humans are involved is really understanding the goals of the systems and the trade-offs, because that is a lot what can exist in a database systems, right? For example, we can be making choices between correctness and speed, or cheap and reliable, and so on and so forth, right? One of the common cheats, for example, in a database space would say, well, you know what, maybe then we are going to commit transactions. We are not going to, let's say, do their distributed commit all around, right? But we are just going to commit it in memory, right? And maybe only commit every few seconds, or at least not replicate transactions to the data center across the world, and so on and so forth, right? That is something which really needs a human direction, which I think AI is not there yet. So another thing on the other hand, where I think AI is a lot better, but which is reality a problem in a lot of human organizations, is the difference between understanding what something needs to be done and actually doing that. In our business, doing consulting, it's very often you come to the organization, say, hey guys, this is what needs to be done. And says, hey, you know what? No, we don't want to do it, right? For or whatever reasons. And again, the AI is not able to really make you do anything. And if anything, probably can be worse than motivating you doing that. I think some of the interesting example in this case would be your, I don't know, how you work out in the gym, for example. If you don't have a human coach, maybe you would not be as persistent as usually. Okay, now let's talk quickly about what kind of architectures we can have. Now, if you look for AI for databases, you can see it designed in kind of two common ways. Is one, it can be overlay the control plane for kind of conventional database, and that can be built into the system. If you look at overlaying, and that means some extra tools for a database, the great thing in this case is what they can use existing database. You don't need to re-architect that completely. You can evolve very quickly, right? But it also have to work with a limited information available which exists in the system. That is, we also need to make sure we have appropriate telemetry which database can provide, and provide that quickly so we can iterate. If you are looking at AI being built as a part of a database kernel, then that is on one side is kind of harder to implement, right? If you can say, well, you know what, instead of us database behaving as it's right now, right, it's automatically, figures out everything instead of you controlling that variables explicitly, right? That would often require a lot of changes to the internal algorithms, right? But at the same time, when you do that, then that means a database can react pretty much in real time. It's not like some external system got data and then reacted on that. And I think that is something which is yet to be done for most of the systems. So far, majority innovation we see is done kind of in the external system. Now, I think another thing what I would highlight, and I think that is what a lot of database experts are worried about, is the fact what AI is kind of hard to understand, especially the most advanced one, right? And often if databases, we want to understand what is happening, why, so we can fix it, we can explain to the boss, right, and so on and so forth, right? And I think getting that level of comfort operating the system we cannot completely explain is something we shall still need to work on. When we speak about the databases right now, I think we still have two approaches to AI trust, right? So when you have those AI tools, in many cases, they would be working with human in the loop, approving the changes, right? And then only some changes you can say, hey, you know what, maybe some light things, you can just do that yourself. For example, there are many databases like which can do after scaling, which is relatively safe, but we are not allowing automatically do some complicated parameter changes or indexes and so on and so forth, right? But in case we do. So if you look at the summary where do we really stand right now? Well, I think if you look at setup can be summarized probably this way. There we can see among the database expert crowd, right, culturally still a lot of unease about how much we can trust AI systems. Now, if you think about what the future brings, I think our ADBA or self-driving database are pretty much, inevitable, right? They are coming, they will be out there. For now, I think it's important to start working with those systems and have those automation to be your best friend. With that, let me finish up by also a couple of other items I have on the list. One is if you guys are interested in their database space, we will have an event focused on that called FOSSASIA University. It's after FOSSASIA Summit on March 11. Would love to see you out there. And the second thing, oh yes, I mean, if the lady just wants to kick me out of here, is we have this little, my sort of like a hobby project where I like to take geeks to suffer in various places. If that is something what you like, please check it out and sign up. And if you, yes, I will follow that guys on the back advice. You say, please, Peter, can you please shut up already, right? Is that what you have written on that sign? Yeah. yes, okay. That's it, thank you.
All right, thank you so much, Peter. Do we have any question for our speaker? All right. If we don't have any question now, please feel free to reach out to Peter after the talk today. I believe like he's gonna very happy to answer the question of everyone. And now this is the closing of the database track today. Thanks a lot for spending time with us. For all of the speakers and all of the attendees who already registered for the community event, we're going to have the community event open in the 6:15 p.m. So don't forget to attend if you already registered for the event. Otherwise, I wish you all have a very good night. Please spend time to hang out with all of the attendees and the speaker into the conference. And I will very happy to welcome you again for tomorrow. Thanks again, everyone.